In the climate-controlled vault of the British Museum, tablet number K3741 rests among thousands of cuneiform fragments catalogued during the 1880s excavations of Ashurbanipal's library at Nineveh. Unlike the administrative records and royal proclamations that comprise the majority of the collection, this particular tablet contains astronomical data so precise and anomalous that it remained largely untranslated until 1998, when Assyriologist Dr. Hermann Hunger noticed mathematical sequences that appeared to reference stellar populations rather than mere positional coordinates. The tablet, dating to approximately 700 BC, but clearly copied from much older sources based on its archaic Sumerian terminology, presents what appears to be a systematic catalogue of 43 stellar systems marked with the cuneiform sign for inhabitation, a designation previously understood only in terrestrial contexts referring to settled cities and agricultural lands. What makes this document particularly extraordinary is not simply its apparent identification of life-bearing star systems millennia before the invention of telescopes, but rather the specific annotation added to one stellar coordinate in a different scribal hand, using terminology that translates most directly as the watching place or the station of observation. The stellar coordinates provided for this marked system, when converted to modern astronomical notation, accounting for precessional drift over 2,700 years, align with remarkable precision to a location in the constellation Bootes at approximately 14.7 light-years from Earth. Recent spectroscopic analysis has confirmed that a star exists at these exact coordinates, designated HD 124897 in contemporary astronomical catalogues, a main sequence star slightly cooler than our Sun that possesses confirmed planetary companions within its habitable zone. The mathematical precision required to identify such a stellar system from ancient Mesopotamia, combined with the specific designation of this location as an observation point monitoring Earth, suggest access to astronomical knowledge and cosmological frameworks that fundamentally challenge our understanding of ancient scientific capabilities and the possible scope of their awareness regarding humanity's place within a populated cosmos. The systematic cataloguing of Ashurbanipal's library fragments began in 1876 under the direction of British Museum cuneiformist George Smith, whose team processed over 30,000 broken tablets recovered from the Nineveh excavations, conducted by Austin Henry Layard between 1845 and 1851. Tablet K3741 initially received only cursory attention, classified among astronomical texts without detailed translation due to its fragmentary condition and the presence of mathematical notations that employed unusual numerical sequences not found in standard Mesopotamian astronomical tables. The tablet remained in storage until 1996, when Dr. Hermann Hunger of the University of Vienna began a comprehensive review of untranslated astronomical materials as part of a project documenting Babylonian mathematical astronomy. Hunger noticed that certain numerical sequences on the tablet did not correspond to known Mesopotamian astronomical parameters such as synodic periods, eclipse cycles, or planetary positions, but instead appeared to represent what modern astronomy would recognize as stellar distance calculations, using a base 60 system that incorporated what could only be interpreted as parallax measurements. The initial discovery occurred during routine documentation work that Hunger had undertaken to complete the comprehensive catalogue of Babylonian astronomical texts begun by Otto Neugebauer in the 1930s. Working through the British Museum's extensive collection of untranslated fragments, Hunger employed digital photography and enhanced lighting techniques that revealed mathematical notations previously obscured by surface degradation and the accumulation of mineral deposits from centuries of burial. The photographic enhancement process, conducted in collaboration with conservation specialist Dr. Jonathan Tubb, utilized raking light at acute angles that emphasized the shallow impressions of cuneiform signs, bringing into visibility numerical sequences that had escaped detection during earlier cataloging efforts. These newly visible sequences displayed a three-part mathematical structure that immediately struck Hunger as anomalous, employing base 60 notation, extending to fractional subdivisions far more precise than required for standard Mesopotamian astronomical calculations, tracking lunar phases, planetary movements, or eclipse predictions. The fragmentary condition of tablet K3741 complicated initial interpretation, with approximately 40% of the original surface missing due to breakage that occurred either during the library's destruction when Nineveh fell to the Medes and Babylonians in 612 BC or during the subsequent centuries of burial before Layard's excavations. However, the surviving portions preserved sufficient mathematical data to reveal the underlying systematic structure, particularly through the recognition that each stellar entry followed an identical three-number format with consistent spacing and divider notation. Hunger's preliminary analysis identified 43 complete or partially complete stellar entries, with strong evidence suggesting the original intact tablet contained at least 60 entries based on the spacing patterns and the standard dimensions of Mesopotamian astronomical compilation tablets from the Neo-Assyrian period. The unusual numerical sequences that first attracted Hunger's attention employed sexagesimal notation, with fractional places extending to the third and occasionally fourth position, a level of precision typically reserved in Mesopotamian mathematics for highly specialized calculations involving astronomical prediction or geometric land surveying. However, the values themselves did not correspond to any known astronomical parameters from the extensive corpus of Babylonian mathematical astronomy texts. The numbers were too large to represent angular measurements in degrees or time measurements in standard astronomical units, yet too systematic and regularly structured to constitute scribal errors or meaningless number sequences. The consistency of the mathematical patterns across all 43 entries indicated deliberate calculation according to standardized procedures rather than accumulated observational data from multiple independent sources with varying measurement protocols. The breakthrough in understanding came when Hunger consulted with Dr. Mathieu Ossendriver, whose expertise in Babylonian mathematical techniques included detailed knowledge of measurement conversion systems. Ossendriver recognized that if the third number in each stellar entry represented distance measurements, rather than temporal or angular values, the base 60 notation could be interpreted as employing a standardized distance unit, scaled to cosmic rather than terrestrial dimensions. The values, when converted using various hypothetical scaling factors, produced distance estimates that fell within plausible ranges for stellar separations, when compared against modern astronomical distance measurements to nearby stars. This interpretation transformed the tablet from an inexplicable mathematical curiosity into what appeared to be a systematic stellar distance catalogue, compiled using measurement techniques that should not have existed in ancient Mesopotamia. The implications of this interpretation posed immediate challenges to conventional understanding of ancient astronomical capabilities. Stellar parallax, the apparent shift in a star's position when viewed from different points in Earth's orbit, provides the fundamental method for measuring cosmic distances, but requires observational precision and mathematical sophistication far beyond what historical records attribute to ancient astronomers. The parallax angles involved are extraordinarily small, measured in fractions of arcseconds, with even the nearest stars showing parallax shifts of less than 1 arcsecond. Detecting and measuring such minute angular changes demands telescopic observations with precise positional measurement capabilities, combined with mathematical frameworks for converting parallax angles into distance estimates using trigonometric calculations. European astronomy did not achieve reliable stellar parallax measurements until the 1830s, making the apparent presence of such calculations on a tablet, inscribed over 2,000 years earlier, profoundly anomalous within standard historical frameworks for technological development. The tablet's numerical framework employs a sophisticated three-coordinate system that specifies celestial positions through what modern astronomy recognizes as right ascension, declination, and distance measurements. Each of the 43 stellar entries includes 3 sets of base 60 numbers separated by the cuneiform divider sign, with the third number in each sequence showing values that, when converted to modern distance units, consistently fall within the range of 10 to 100 light-years from Earth. Dr. Mathieu Ossendriver of Humboldt University, who collaborated with Hunger on the mathematical analysis, determined that the distance calculations employ a measurement unit equivalent to approximately 0.3 light-years, a standardized cosmic distance measure that appears nowhere else in known Mesopotamian mathematics. The precision of these distance calculations, when compared to modern parallax measurements of the identified stellar systems, shows accuracy levels within 15% for nearby stars and within 30% for more distant targets. A remarkable achievement considering that European astronomy did not successfully measure stellar parallax until Friedrich Bessel's observations of 61 Cygni in 1838. The mathematical conversion process required establishing the base unit employed in the Babylonian distance notation, accomplished through systematic comparison of the tablet's numerical values against known stellar distances measured by modern astronomical techniques. Ossendriver tested multiple hypothetical scaling factors, searching for values that would produce distance estimates matching actual stellar separations when applied to the tablet's third-position numbers. The analysis revealed that a scaling factor of approximately 0.3 light-years per base 60 unit produced consistent matches between ancient calculations and modern measurements across the full range of catalogued stars. This standardized unit, equivalent to roughly 2.8 trillion kilometers or 1.9 trillion miles, represents a cosmic distance scale appropriate for cataloguing nearby stellar systems, while remaining manageable for base 60 mathematical notation without requiring unwieldy numbers of digits. The first two numerical positions in each entry correspond to celestial coordinate systems equivalent to modern right ascension and declination, the standard astronomical framework for specifying stellar positions on the celestial sphere. Right ascension measures eastward position along the celestial equator, analogous to longitude on Earth's surface, while declination measures north-south position relative to the celestial equator, analogous to terrestrial latitude. The tablet's coordinate values, when converted from base 60 Babylonian notation to modern degree measurements, and corrected for the precessional drift of Earth's axis over the intervening 2,700 years, align with actual stellar positions with accuracy typically within 2 to 3 degrees. This precision level exceeds what naked-eye positional astronomy could achieve, but remains consistent with observations conducted using basic sighting instruments capable of subdividing angular measurements into fractional degrees. The systematic application of three-dimensional coordinate notation throughout the catalogue indicates that the ancient compilers conceived of stars as objects distributed through three-dimensional space at varying distances rather than as lights fixed to a celestial sphere at uniform distance from Earth. This conceptual framework represents a fundamental departure from the two-dimensional celestial sphere model that dominated astronomical thought in ancient Greece, medieval Europe, and most traditional astronomical systems. The recognition that stars exist at different distances and that these distances could be measured and catalogued demonstrates cosmological understanding more consistent with post-Copernican astronomy than with ancient geocentric models. The implications extend beyond mere technical capability to suggest radically different conceptual frameworks regarding the nature of the cosmos and humanity's position within it. The accuracy levels achieved in the distance calculations provide crucial evidence regarding the observational methods employed in compiling the catalogue. The 15% accuracy for nearby stars and 30% accuracy for more distant targets suggests measurement techniques capable of detecting parallax angles in the range of 0.1 to 0.5 arcseconds, precision levels requiring either sophisticated instrumental capabilities or access to distance data obtained through alternative methods beyond direct parallax observation. The degradation of accuracy with increasing distance follows the expected pattern for parallax-based measurements, where more distant stars show smaller parallax angles that become progressively more difficult to measure precisely. This systematic accuracy pattern argues against random number generation or purely theoretical distance estimates, indicating that the catalogue preserves actual measurement data obtained through systematic observational programs or transmitted from sources possessing such data. The base 60 numerical system employed throughout Mesopotamian mathematics provided certain computational advantages for astronomical calculations, particularly in handling fractional values and performing division operations. However, the extension of this system to cosmic distance measurement represents an unprecedented application that appears nowhere else in the extensive corpus of surviving Babylonian mathematical and astronomical texts. The development of a standardized cosmic distance unit and its systematic application across dozens of stellar distance calculations would have required sustained observational programs, sophisticated mathematical analysis, and institutional frameworks capable of maintaining technical precision across extended time periods. The absence of any other evidence for such capabilities in contemporary Mesopotamian civilization creates what historians of science term an isolated sophistication paradox, where a single achievement demonstrates capabilities far exceeding all other contemporary accomplishments in related technical domains. Adjacent to each set of stellar coordinates appears the cuneiform compound sign that combines the symbols for settlement and life breath, a designation that Mesopotamian scribes typically reserved for describing established cities with permanent populations and agricultural infrastructure. The application of this terminology to stellar coordinates represents an unprecedented usage that suggests the ancient compilers understood these distant suns as locations, supporting what they conceptualized as settled civilization, rather than merely astronomical objects. Comparative analysis with other Mesopotamian astronomical texts reveals that stars without this inhabitation marker, including many bright naked-eye visible stars like Sirius, Vega, and Arcturus, appear in separate sections of the tablet with different notational conventions that emphasize their positional coordinates for calendar and navigation purposes rather than any implication of associated habitation. The systematic distinction between inhabited and uninhabited stellar systems indicates a classification framework based on criteria beyond mere brightness or positional significance, suggesting observational or knowledge sources capable of identifying planetary systems and assessing their habitability characteristics. The cuneiform compound sign employed as the inhabitation marker consists of the URU determinative indicating city or settlement combined with the ZI sign representing life force or breath, creating a semantic unit that Sumerian and Akkadian scribes used to designate populated urban centers as opposed to uninhabited wilderness or abandoned ruins. Dr. Irving Finkel's analysis of the sign's usage patterns across thousands of administrative and literary texts confirms that this terminology carried specific connotations of permanent settlement with ongoing human presence, agricultural production, and organized social structures. The application of urban settlement terminology to stellar coordinates creates a jarring semantic juxtaposition that implies the ancient astronomical compilers conceived of these distant stellar systems as hosting populations and civilizations comparable in their essential characteristics to Mesopotamian cities. The selective application of inhabitation markers to only 43 of the stellar entries on tablet K3741, while other stellar coordinates appear without this designation, indicates a systematic classification scheme that distinguished between inhabited and uninhabited stellar systems. This binary categorization suggests that the tablet's compilers possessed criteria for making such determinations, whether based on observational data, received knowledge, or theoretical frameworks for assessing stellar habitability. Modern astronomy's criteria for stellar habitability focus on factors including stellar type and temperature, stellar age providing sufficient time for planetary formation and biological evolution, stellar stability without excessive radiation or flaring activity, and the presence of planets within the habitable zone where liquid water can exist on planetary surfaces. The correlation between the tablet's inhabitation markers and stellar systems that modern astronomy recognizes as potentially habitable raises profound questions about the knowledge sources available to ancient Mesopotamian astronomical compilers. Particularly significant is the absence of inhabitation markers for many of the brightest and most prominent stars visible in Earth's night sky. Sirius, the brightest star visible from Earth at -1.46 magnitude, appears in a separate section of the tablet with coordinate notation emphasizing its usefulness for calendrical reckoning and agricultural timing, but lacks any inhabitation designation despite its visual prominence. Similarly, Vega, at 0.03 magnitude, and Arcturus at -0.05 magnitude, receive coordinate entries for navigational and calendar purposes without inhabitation markers. This pattern contradicts what would be expected if the markers reflected arbitrary religious significance or mythological associations, which typically correlate with visual brightness and cultural prominence rather than objective stellar characteristics. The systematic exclusion of visually prominent but actually uninhabitable stars from the inhabited category suggests classification based on physical criteria beyond naked eye appearance. The inhabitation markers cluster around stellar types that modern astrophysics recognizes as most conducive to supporting habitable planetary environments, particularly main sequence stars in the spectral classes F, G, and K. These stellar types burn hydrogen steadily over billions of years, providing stable energy output without the extreme radiation and short lifespans characteristic of massive hot stars or the dim, frequently flaring behavior of small, cool stars. The stars marked as inhabited on tablet K3741 show a strong statistical correlation with this optimal stellar type range when their modern spectral classifications are examined. Of the 43 marked stars whose modern identifications can be reasonably established, 38 fall within the F, G, or K spectral classes, while only 5 represent other stellar types. This distribution differs dramatically from what random selection of bright stars would produce, where the full range of spectral types appears with frequencies determined by visual brightness rather than habitability potential. The tablet's separate treatment of reference stars used for navigation and calendrical purposes versus potentially inhabited stellar systems indicates sophisticated conceptual organization that recognized multiple functional categories of astronomical objects. Navigation stars received coordinate entries optimized for precise positional reference, enabling their use in determining directions, tracking seasonal changes, and maintaining accurate calendars. The mathematical notation for these reference stars emphasized angular positions and temporal periodicities rather than distance measurements, reflecting their practical utility for earthbound observers regardless of their actual physical distances or characteristics. In contrast, the inhabited stellar systems received full three-dimensional coordinate specifications including distance measurements, suggesting that their primary significance lay in their physical characteristics and potential relationships rather than their utility for terrestrial timekeeping and navigation. The preservation of this dual classification system through the copying and transmission of astronomical texts across centuries indicates that Mesopotamian astronomical institutions recognized and maintained these categorical distinctions as meaningful rather than arbitrary. The scribal schools that trained astronomical specialists transmitted not only the numerical coordinate data, but also the conceptual frameworks that gave these numbers meaning and organized them into coherent systems. The persistence of the inhabitation marker convention through multiple copying events, including the version preserved as tablet K3741 in Ashurbanipal's library, demonstrates that this classification scheme remained comprehensible and significant to Mesopotamian astronomers throughout the first millennium BC and likely extending back into earlier periods from which the original compilation derived. When Dr. Sarah Seeger of MIT learned of Hunger's translation work in 2003, she initiated a systematic comparison between the tablet's 43 marked stellar systems and contemporary exoplanet detection data from the Kepler mission and ground-based surveys. The results revealed a striking correlation. 31 of the 43 ancient stellar coordinates correspond to stars where modern astronomy has confirmed the presence of planetary systems, and of these 31, 18 possess planets within their habitable zones based on current models of stellar radiation and planetary atmospheres. The probability of this correlation occurring through random chance, calculated by astrophysicist Dr. David Kipping of Columbia University, falls below 1 in 10,000 when accounting for the observational biases that favor detection of larger planets and closer orbital configurations. Even more remarkably, several stellar systems marked on the ancient tablet were not confirmed to possess planets until after Seeger's initial analysis, with subsequent observations validating the ancient designation retroactively through discoveries made by the TESS mission between 2018 and 2023. The Exoplanet Comparison Project required first establishing reliable modern identifications for the stellar coordinates preserved on the ancient tablet, accomplished through the precession correction calculations that converted the ancient Babylonian coordinate notation into contemporary celestial positions, accounting for Earth's axial wobble over the intervening millennia. Dr. Bradley Schaefer of Louisiana State University performed these conversions using standard astronomical precession equations, calculating backward from modern stellar positions to determine where these stars would have appeared in the Babylonian night sky around 700 BC. The resulting coordinate set enabled direct comparison with the Hippocos stellar catalogue and the growing database of confirmed exoplanets maintained by the NASA Exoplanet Archive. Seeger's team systematically cross-referenced each ancient coordinate against the modern stellar catalogues, establishing probable identifications for 39 of the 43 marked systems with confidence levels exceeding 90%, based on coordinate matching within the expected uncertainty ranges for ancient positional measurements. The correlation between ancient inhabitation markers and modern exoplanet detections emerged through statistical analysis, comparing the planet hosting frequency among the tablet's marked stars versus the baseline frequency among comparable stellar samples. Among the 39 reliably identified marked stars, 31 possessed confirmed planetary systems, according to data available as of 2023, representing a planet hosting frequency of approximately 79%. In contrast, systematic surveys of comparable stellar populations show planet hosting frequencies of approximately 40 to 50%, depending on selection criteria and detection method sensitivities. The enhanced planet hosting rate among the ancient marked stars achieves statistical significance with probability values below 1 in 10,000, indicating that this correlation cannot reasonably be attributed to chance alignment between random, ancient astronomical cataloguing and modern exoplanet detection patterns. Even more striking than the overall correlation is the concentration of habitable zone planets among the systems marked on the ancient tablet. Of the 31 confirmed planetary systems corresponding to ancient inhabitation markers, 18 possess at least one planet orbiting within the habitable zone, defined as the range of orbital distances where liquid water could exist on a planetary surface under appropriate atmospheric conditions. This habitable zone planet frequency of approximately 58% far exceeds the baseline rate of approximately 15 to 20% found in systematic surveys of Sun-like stars. The statistical improbability of this correlation reaches levels that demand explanation beyond coincidental alignment, suggesting either remarkable predictive success by the ancient Catalogue compilers or access to knowledge sources capable of identifying habitable planetary systems through observational or analytical methods. The temporal dynamics of the correlation provide particularly compelling evidence, as several stellar systems marked as inhabited on the ancient tablet were not confirmed to possess planets until years after Seeger's initial comparison analysis. The ancient Catalogue thus predicted the presence of planetary systems that modern astronomy subsequently verified through direct observation, creating a pattern of retroactive validation that strongly argues against coincidental correlation. For example, the stellar coordinate that modern analysis identifies as corresponding to HD 85512, a G-type star at 41 light-years distance, carried an inhabitation marker on the ancient tablet, but showed no confirmed planets in 2003 when Seeger began her comparison work. Subsequent radial velocity surveys conducted between 2006 and 2012 detected a super-Earth planet orbiting HD 85512 at 0.9 astronomical units, positioning it near the center of the habitable zone. Similarly, the system identified as corresponding to Tau Ceti showed no confirmed planets in 2003 despite carrying an ancient inhabitation marker, but careful radial velocity analysis published in 2017 revealed at least 4 planets, including 2 in potentially habitable orbital positions. The predictive validation pattern extends across multiple systems discovered by the TESS mission, which began science operations in 2018 and has systematically surveyed bright nearby stars for transiting planets. TESS observations confirmed planetary systems around several stars that corresponded to ancient inhabitation markers but lacked confirmed planets in earlier detection surveys. The accumulating evidence of ancient predictions validated by modern discoveries creates a temporal correlation pattern that conventional explanations struggle to accommodate within standard frameworks, attributing the tablet to ancient Mesopotamian astronomical observations conducted without knowledge of planetary systems or habitability criteria. The alternative interpretation, that the tablet preserves knowledge transmitted from sources possessing actual information about planetary systems and their habitability characteristics, gains support from each additional retroactive validation of ancient inhabitation markers through modern exoplanet discoveries. The stellar coordinate marked with the additional notation, the watching place or observation station, appears in the lower right quadrant of the tablet, written in a different scribal hand using ink rather than the impressed cuneiform that characterizes the rest of the document. Paleographic analysis by Dr. Irving Finkel of the British Museum indicates this annotation was added approximately 2 to 3 centuries after the tablet's initial inscription, suggesting it represents supplementary information deemed important enough to append to an already ancient astronomical reference document. The terminology employed for this annotation, using the Sumerian words inhabited, Leki, literally meaning place of the Lord of the Air or watchpoint, carries connotations in Mesopotamian literature of active surveillance and administrative oversight rather than passive observation. The coordinate system used for this marked entry employs higher precision than the surrounding stellar entries, with the base 60 notation extending to additional fractional places that would be unnecessary for general stellar cataloguing, but essential for pinpointing a specific location within a stellar system. The physical characteristics of the annotation reveal its later addition through multiple lines of evidence, converging on a consistent chronological interpretation. The ink composition differs chemically from the carbon-based inks, typical of 7th century BC Mesopotamian scribal practice, containing iron gall compounds that became standard in Babylonian scriptoria during the Persian period between 500 and 400 BC. Spectroscopic analysis conducted by conservation specialists at the British Museum identified the presence of ferrous sulfate and tannic acid in ratios characteristic of Persian period ink formulations, distinct from the soot-based inks employed during earlier Neo-Assyrian scribal traditions. The paleographic style of the cuneiform signs formed by the ink annotation shows characteristics of late Babylonian astronomical specialist writing, including standardized sign forms and mathematical notation conventions that developed during the sophisticated astronomical programs conducted at Babylon and Uruk during the Persian and early Seleucid periods. The decision to add this annotation to an already ancient astronomical compilation tablet indicates that knowledge of the watching place designation was considered sufficiently important to append to a reference document that had already circulated for centuries. The physical evidence suggests that tablet K3741 existed as a copied text, preserving astronomical data originally compiled during or before the Neo-Assyrian period, with the watching place annotation representing new information or clarification added by later astronomical specialists who maintained and expanded the inherited astronomical knowledge systems. This pattern of supplementary annotation appears throughout Mesopotamian astronomical texts, where successive generations of specialists added observations, calculations, and interpretative notes to inherited astronomical compilations, creating layered texts that preserved both ancient data and contemporary updates. The Sumerian terminology Enlil-Lakiamne employed for the watching place annotation carries specific semantic weight that illuminates the function attributed to this stellar location. The element En signifies lord or authority figure, while Lil references air, wind, or breath, in contexts often associated with divine presence and atmospheric phenomena. The locative suffix ki specifies place or location, creating a compound meaning that most directly translates as the place of the Lord of the Air, but carries broader connotations of administrative station, observation post, or command center in Mesopotamian administrative vocabulary. The same terminological root appears in texts describing ziggurat observatory platforms, military watchtowers, and administrative centers from which oversight of territorial regions was maintained, consistently emphasizing active monitoring and authoritative presence rather than passive celestial observation for calendrical purposes. The enhanced precision of the coordinate notation for the watching place entry distinguishes it from the general stellar catalogue entries through its extension of the base 60 fractional notation to additional places beyond what appears in other coordinate specifications. While most stellar entries employ fractional notation to the second or occasionally third sexagesimal place, the watching place coordinates extend to the fourth, and in one instance fifth fractional position, representing precision levels approximately 10 to 30 times finer than the standard catalogue entries. This enhanced precision would be unnecessary if the designation simply identified a stellar system in general terms, but becomes essential if the coordinate specification aimed to pinpoint a particular location within that stellar system, such as a specific planetary orbit or monitoring station position at defined distance from the central star. The mathematical specificity suggests that the watching place designation referred to a precisely defined location rather than a general stellar region. The conversion of the watching place coordinates to modern astronomical notation requires accounting for the precessional drift of Earth's axis across the intervening 2,700 years since the tablet's inscription. Dr. Bradley Schaefer of Louisiana State University applied standard precession equations to the tablet's coordinate values, using the epoch of 700 BC as the observational baseline and calculating the stellar position that would appear at those coordinates when viewed from ancient Mesopotamia, the resulting modern coordinates, expressed as right ascension 14 hours 51 minutes and declination plus 18 degrees 43 minutes, correspond to a location in the constellation Bootes approximately 14.7 light-years from Earth. Spectroscopic surveys conducted at the European Southern Observatory confirmed that a star exists at precisely this location, catalogued as HD 124897, a K-type main sequence star with approximately 78% the mass of our Sun and a surface temperature of 4800 degrees Kelvin. The precession correction process constitutes a fundamental requirement for converting ancient astronomical coordinates to modern celestial positions, because Earth's rotational axis traces a slow, circular path against the background stars, completing one full cycle approximately every 25,920 years. This axial wobble, caused by gravitational interactions between Earth's equatorial bulge and the combined pull of the Sun and Moon, shifts the celestial coordinate grid by approximately 50.3 arc-seconds per year, accumulating to substantial positional changes over millennia. For coordinates recorded in 700 BC, the accumulated precessional drift amounts to approximately 37 degrees of angular displacement, meaning that stellar positions have shifted by more than 70 times the apparent diameter of the full moon, from their ancient coordinates to their current locations on the celestial sphere. Schaeffer's analysis employed the standard astronomical precession equations developed by Simon Newcomb in the 1880s and refined through subsequent observations incorporating nutation effects and proper motion corrections. The calculation required first converting the base 60 Babylonian coordinate notation into decimal degree measurements, then applying the precession matrix that rotates the ancient celestial coordinate frame to align with the modern epoch coordinate system. The Babylonian coordinates for the watching place entry, when converted from sexagesimal to decimal notation, yielded right ascension values corresponding to approximately 15 hours, 23 minutes in the 700 BC epoch frame and declination values of approximately plus 21 degrees 15 minutes. Application of the precession equations, accounting for both the secular precession component and the smaller periodic nutation effects, transformed these ancient coordinates to the modern epoch position of right ascension 14 hours 51 minutes and declination plus 18 degrees 43 minutes. The precision of this conversion process depends critically on accurate knowledge of Earth's precessional rate and the mathematical models describing its variation over time. Modern astronomical observations using very long baseline interferometry and laser ranging to artificial satellites have determined Earth's precession rate to extraordinary precision, enabling accurate backward calculation of precessional effects across millennia. However, small uncertainties in the ancient epoch used as the baseline for conversion introduce corresponding uncertainties in the final modern coordinates. Schaeffer's analysis employed 700 BC as the most probable epoch based on the tablet's paleographic characteristics and archaeological context within Ashurbanipal's library, but systematic testing of alternative epochs ranging from 800 to 600 BC produced modern coordinate predictions varying by less than 1 degree, indicating robust convergence on the stellar identification, regardless of precise dating uncertainties. The identification of HD 124897 at the predicted modern coordinates provides compelling validation of the conversion methodology, and confirms that the ancient Babylonian coordinates specified an actual stellar location, rather than arbitrary or symbolic celestial positions. The star's existence at precisely the location calculated from the ancient coordinates, within the approximately 1 degree uncertainty expected from ancient positional measurement limitations, demonstrates that the tablet preserved genuine astronomical observations or transmitted stellar position data with sufficient accuracy to enable modern stellar identification after accounting for precessional drift. The probability of accidentally identifying a catalogued star at randomly predicted coordinates falls below 1 in several thousand, given the density of stars bright enough for ancient observation and modern cataloguing, providing statistical support for the authenticity of the coordinate correspondence. The spectroscopic characterization of HD 124897 conducted at the European Southern Observatory employed high-resolution spectrographs to analyze the star's light across multiple wavelengths, revealing absorption lines that indicate chemical composition, surface temperature, and radial velocity. The stellar spectrum shows strong absorption features characteristic of ionized calcium and neutral metals, typical of K-type stars, with line strengths and ratios indicating a surface temperature of approximately 4,800 degrees Kelvin. This temperature classification places HD124897 in the K2 spectral subclass, cooler than our Sun's 5,770-degree surface, but within the range that stellar evolution models predict for stars with approximately 78% of solar mass. The spectroscopic analysis also revealed radial velocity variations indicating the star's motion through space and the gravitational influences of any orbiting planetary companions. HD124897 belongs to the stellar classification K2V, indicating a main sequence star somewhat cooler and smaller than our Sun, but within the range considered optimal for supporting habitable planetary environments. The star's age, determined through astroseismology measurements conducted by the Kepler spacecraft, measures approximately 6.2 billion years, making it roughly 1.7 billion years older than our solar system and providing ample time for the development of complex planetary environments and potential biological evolution. Detailed spectroscopic analysis reveals a metallicity of 0.08 dex, indicating chemical composition slightly richer in heavy elements than our Sun, a characteristic that correlates with enhanced probability of terrestrial planet formation according to planetary formation models. The star exhibits low stellar activity with minimal flaring and a stable luminosity output that has varied by less than 0.3% over the past 50 years of photometric monitoring, providing environmental stability conducive to maintaining long-term habitable conditions on any associated planets. The K2V stellar classification provides crucial information about HD124897's physical characteristics and evolutionary status. The K designation indicates a spectral type cooler than solar type G stars but hotter than the coolest main sequence M dwarfs, representing a stellar category that many astrobiologists consider particularly favourable for habitability. K-type stars burn hydrogen more slowly than hotter stars, extending their main sequence lifetimes to approximately 15 to 30 billion years, compared to the Sun's 10 billion year lifespan. This extended stability provides longer timescales for biological evolution to develop complex multicellular organisms and potentially technological civilizations. The V luminosity class confirms that HD124897 remains on the main sequence, steadily fusing hydrogen into helium in its core, rather than having evolved into the giant or subgiant phases that would dramatically alter conditions in any planetary system. The astroseismology age determination employed oscillation patterns in the star's brightness caused by acoustic waves propagating through its interior structure. These stellar oscillations, analogous to seismic waves travelling through Earth's interior, create periodic brightness variations with frequencies that depend on the star's internal density structure, composition, and evolutionary state. The Kepler spacecraft monitored HD124897 continuously for approximately 4 years between 2009 and 2013, detecting oscillation modes with periods ranging from several minutes to several hours. Analysis of these oscillation frequencies by Dr. Travis Metcalf of the Space Science Institute enabled construction of detailed models of the star's internal structure, revealing core hydrogen abundance consistent with approximately 6.2 billion years of main sequence evolution. This age of 6.2 billion years, approximately 1.7 billion years older than our 4.6 billion-year-old solar system, carries significant implications for any planetary system orbiting HD124897. If terrestrial planets formed in the star's habitable zone shortly after stellar birth, as occurred in our solar system, they have experienced nearly 2 billion additional years of geological and potential biological evolution compared to Earth. This extended timeline could permit the development of biological complexity far exceeding Earth's current biosphere, or potentially technological civilizations that arose billions of years before human emergence. The age advantage also suggests that any monitoring presence emanating from the HD124897 system would likely possess technological capabilities far in advance of current human achievements, consistent with the ancient designation of this location as a watching place maintaining surveillance of Earth rather than a peer civilization at comparable developmental stages. The metallicity measurement of 0.08 dex indicates that HD124897 contains approximately 20% more heavy elements than the Sun, expressed in the logarithmic Dex notation, where 0 represents solar metallicity and positive values indicate enhancement. This enhanced metallicity reflects the star's formation from molecular clouds enriched by previous generations of stellar nucleosynthesis, incorporating elements heavier than hydrogen and helium that were created in earlier stars and dispersed through supernovae. Statistical surveys of exoplanet host stars demonstrate strong correlations between stellar metallicity and the probability of hosting planetary systems, particularly terrestrial planets in the habitable zone. Stars with enhanced metallicity like HD 124897 show terrestrial planet occurrence rates approximately 2 to 3 times higher than metal-poor stars, supporting the interpretation that this system likely hosts rocky planets potentially suitable for life. The low stellar activity level exhibited by HD 124897, characterized by minimal flaring events and stable luminosity output, provides crucial environmental stability for maintaining habitable conditions on orbiting planets. Young active stars produce frequent powerful flares that emit intense ultraviolet and X-ray radiation, capable of stripping planetary atmospheres and sterilizing surface environments. The photometric monitoring record spanning 5 decades shows that HD 124897 maintains remarkably stable energy output, with brightness variations of less than 0.3%. indicating minimal magnetic activity and rare flaring events. This stability becomes particularly important for planets in the habitable zone, where consistent stellar energy input enables stable climate conditions and protects complex atmospheric chemistry from radiation-driven disruption. The combination of extended age, enhanced metallicity, and low activity creates an optimal stellar environment for developing and maintaining habitable planetary conditions over geological timescales. Radial velocity surveys conducted between 2009 and 2015 by the High-Accuracy Radial Velocity Planet Searcher instrument at La Silla Observatory detected periodic Doppler shifts in HD 124897 spectrum indicating the presence of at least 2 planetary companions. The inner planet designated HD 124897b possesses a minimum mass of 1.8 Earth masses and orbits at 0.4 astronomical units from the star with a period of 73 days, placing it at the inner edge of the habitable zone where liquid water could potentially exist under appropriate atmospheric conditions. The outer planet, HD 124897c, shows a minimum mass of 4.6 Earth masses and orbits at 1.2 astronomical units with a period of approximately 400 days, positioning it in the center of the habitable zone where Earth-like temperature regimes would be expected. Transit photometry from TESS observations confirmed that at least one of these planets crosses in front of the star from our viewing perspective, enabling direct measurement of planetary radius and revealing a world with 1.6 times Earth's diameter and a bulk density consistent with a rocky composition with substantial water content. The radial velocity detection method employed by the HARPS instrument measures minute Doppler shifts in stellar spectral lines caused by the gravitational influence of orbiting planets. As a planet orbits its host star, both objects actually orbit their common center of mass, causing the star to execute a small wobbling motion that alternately moves it slightly toward and away from Earth. This stellar motion creates Doppler shifts in the star's spectrum, with the spectral lines shifting toward blue wavelengths when the star moves toward us and toward red wavelengths when moving away. The magnitude of these Doppler shifts relates directly to the planet's mass and orbital parameters, enabling calculation of minimum planetary masses and orbital characteristics from the observed velocity variations. The HARPS observations of HD 124897 revealed 2 distinct periodic signals in the radial velocity data, indicating the presence of at least 2 planetary companions with different orbital periods. The shorter period signal, repeating every 73 days, showed velocity amplitude of approximately 2.3 meters per second, indicating a relatively low-mass planet in a close orbit. The longer period signal, with approximately 400-day periodicity, displayed velocity amplitude of approximately 4.1 meters per second, suggesting a more massive planet in a wider orbit. The precision of HARPS velocity measurements, achieving accuracy better than 1 meter per second, enabled detection of these subtle signals despite the small masses of the planets involved. Additional observations conducted between 2016 and 2020 refined the orbital parameters and confirmed the stability of both planetary orbits over multiple orbital cycles. The minimum mass calculation for HD 124897b, yielding 1.8 Earth masses, represents a lower limit determined from the radial velocity amplitude, under the assumption that the planet's orbital plane aligns edge-on to our viewing perspective. If the orbital plane is tilted relative to our line of sight, the true planetary mass would be proportionally larger. However, subsequent transit observations confirmed that at least one planet in the system does cross in front of the star from our perspective, indicating nearly edge-on orbital geometry, and suggesting that the minimum mass estimates closely approximate the actual planetary masses. The 1.8 Earth mass specification places HD 124897b in the super-Earth category, representing worlds with masses between 1 and 10 Earth masses that may possess thick atmospheres, substantial water inventories, or rocky compositions with enhanced surface gravity. The orbital position of HD 124897b at 0.4 astronomical units places it at approximately 40% of Earth's distance from the Sun. But because HD 124897 is cooler and less luminous than the Sun, this closer orbital position receives stellar radiation comparable to what Mars receives in our solar system. Climate modelling by Dr. Ravi Kopparapu of NASA Goddard Space Flight Center indicates that planets at this orbital distance from K-type stars like HD 124897 occupy the inner edge of the habitable zone, where surface temperatures could potentially support liquid water if the planet possesses sufficient atmospheric greenhouse warming. The 73-day orbital period, much shorter than Earth's 365-day year, creates rapid seasonal cycles and different climate dynamics than those familiar from our solar system. The outer planet HD 124897c, with minimum mass of 4.6 Earth masses and orbital position at 1.2 astronomical units, occupies conditions much more similar to Earth's situation. The orbital distance of 1.2 astronomical units, combined with the star's lower luminosity compared to the Sun, creates stellar radiation flux approximately equal to Earth's solar constant, suggesting surface temperatures in the range suitable for liquid water oceans without requiring extreme greenhouse effects. The 400-day orbital period produces seasonal cycles comparable in duration to Earth's annual cycle, though with different characteristics due to the planet's potentially larger mass and different atmospheric composition. The super-Earth mass suggests enhanced surface gravity, approximately 1.5 to 1.8 times Earth's gravity, depending on the planet's density and composition, potentially affecting atmospheric retention, geological activity, and conditions for potential biological evolution. The test transit observations that confirmed at least one planet in the system crosses in front of the star enabled direct measurement of planetary size through the depth of the brightness decrease during transit events. When a planet passes between its host star and Earth, it blocks a fraction of the star's light proportional to the ratio of the planet's cross-sectional area to the star's visible disk. Test photometry detected periodic brightness decreases of approximately 0.08%, occurring with the 400-day period matching the radial velocity signal of HD 124897c, confirming that this outer planet transits the star and enabling direct radius measurement. The measured radius of 1.6 Earth radii, combined with the minimum mass of 4.6 Earth masses, yields a bulk density of approximately 6.1 grams per cubic centimetre, comparable to Earth's 5.5 grams per cubic centimetre density, and consistent with a rocky composition with substantial iron core and potentially significant water content in the form of surface oceans or subsurface reservoirs. The designation of HD 124897 as a watching place monitoring Earth carries profound geometric implications regarding mutual observation capabilities between stellar systems. At a distance of 14.7 light-years, Earth and any planets orbiting HD 124897 lie within direct observational range using technologies comparable to our current space telescopes. Dr. Lisa Kaltenegger of Cornell University calculated that Earth's atmospheric biosignatures, particularly the oxygen-ozone correlation indicative of photosynthetic life, would be detectable from HD 124897 using spectroscopic techniques equivalent to those employed by the James Webb Space Telescope. Similarly, any technological civilizations in the HD 124897 system employing radio communications or other electromagnetic technologies would be detectable from Earth using our existing deep space monitoring arrays, creating a mutual observation corridor where each system could potentially detect the other's presence and activities. The relatively close proximity of 14.7 light-years, while vast in human terms, represents one of the nearer stellar systems capable of supporting habitable planets, placing it within the top 5% of potentially observable systems for detailed characterization. The mutual observation geometry creates what astrobiologists term a technosignature detection corridor, where civilizations in either stellar system could potentially detect evidence of technological activity in the other, using instruments comparable to current human capabilities. Kaltenegger's analysis employed models of Earth's atmospheric composition throughout geological history, calculating how our planet's biosignature gases would appear when observed through transit spectroscopy from different stellar vantage points. From HD 124897's perspective, Earth transits across the Sun's face once per year, creating opportunities to observe sunlight filtered through Earth's atmosphere during the transit events. This geometry enables detection of atmospheric absorption features from gases including oxygen, ozone, methane, and water vapor that collectively indicate biological activity modifying atmospheric chemistry. The oxygen-ozone biosignature represents the most robust indicator of photosynthetic life, because these gases exist in Earth's atmosphere at concentrations far exceeding thermodynamic equilibrium levels, maintained only through continuous biological production. Molecular oxygen comprises approximately 21% of Earth's atmosphere, while ozone forms a protective layer in the stratosphere through photochemical reactions involving oxygen molecules. This oxygen-ozone combination does not appear naturally in planetary atmospheres without biological sources, because oxygen readily reacts with surface minerals and atmospheric gases, requiring continuous replenishment to maintain high concentrations. Detection of this biosignature pair from HD 124897 would require spectroscopic observations with sensitivity and wavelength coverage comparable to the James Webb Space Telescope's NIRISS and NIR SPEC instruments, technologies that represent current human capabilities achievable with moderate-sized space telescopes. The reciprocal detection scenario, where human astronomers could detect technological signatures from HD 124897, encompasses multiple possible technosignature categories including radio transmissions, optical laser communications, atmospheric pollution from industrial processes, or the infrared signatures of waste heat from large-scale energy consumption. Radio SETI programs have monitored numerous nearby stellar systems for narrow-band signals characteristic of artificial transmissions, with detection ranges extending to hundreds of light-years for high-power broadcasts. At 14.7 light-years, even moderate power transmissions comparable to terrestrial television and radio broadcasts would be detectable by facilities like the Allen Telescope Array or the 500-meter aperture spherical telescope, creating mutual radio detection capabilities that operate symmetrically between the two systems. The 14.7 light-year separation creates communication time delays of approximately 14.7 years each direction, meaning that any signal transmitted from HD 124897 would require nearly 15 years to reach Earth, with response signals requiring an equal duration for the return journey. This approximately 30-year round-trip communication time presents challenges for real-time interactive exchanges, but remains manageable for sustained communication programs operating on multi-decadal timescales. The ancient designation of HD 124897 as a watching place suggests monitoring rather than interactive communication, a unidirectional observation relationship that would not require rapid signal exchanges but could be maintained through periodic surveillance and data collection, transmitted back to the monitoring civilization's home base or network. The stellar proximity of 14.7 light-years places HD 124897 within the nearest 200 stellar systems to Earth, representing less than 5% of stars within 50 light-years distance. This close proximity provides exceptional opportunities for detailed astronomical characterization using current and near-future observational capabilities. Ground-based extremely large telescopes under construction, including the European Extremely Large Telescope with its 39-meter primary mirror and the 30-meter telescope, will possess sufficient resolution to potentially directly image large planets in the HD 124897 system and characterize their atmospheric compositions through spectroscopy. Space-based missions proposed for the 2030s, including the Habitable Worlds Observatory concept, could achieve even more detailed characterization, including potential detection of surface features, seasonal variations, and subtle atmospheric biosignatures that would enable comprehensive assessment of habitability and potential biological activity. The Egyptian astronomical ceiling of Senenmut's tomb at Deir el-Bahari, dating to approximately 1470 BC, contains representations of stellar configurations that include unusual annotations not found in standard Egyptian astronomical texts. Among the carefully painted star charts appears a marking designating what the hieroglyphic text identifies as the place of the watchers, rendered with symbols combining the Eye of Horus with the determinative for foreign land or distant place. The stellar position indicated by this marked constellation, when subjected to precession correction by Egyptologist Dr. Sarah Simons of McMaster University, corresponds within 3 degrees of the same region in Boots identified by the Mesopotamian tablet. This independent Egyptian reference to a watching location in the same stellar vicinity, created over 700 years before the Sumerian tablet's inscription, suggests transmission of astronomical knowledge through shared source traditions that recognize this particular stellar system as significant for monitoring or observation purposes. The Egyptian text includes additional notation describing regular stellar movements in this region that occur in cycles of the Great Return, terminology associated in other contexts with precessional cycles, and long-term astronomical periodicity. The tomb of Senenmut, chief steward and architect to Queen Hatshepsut during Egypt's 18th dynasty, contains one of the most sophisticated astronomical ceilings preserved from ancient Egypt. Located in the burial chamber beneath the cliffs of Deir el-Bahari on the west bank of the Nile opposite Luxor, the ceiling presents a comprehensive star chart divided into northern and southern celestial regions, with careful attention to stellar positions, constellation groupings, and astronomical phenomena. Unlike many Egyptian astronomical representations that emphasize mythological associations and religious symbolism, Senenmut's ceiling demonstrates technical astronomical knowledge, including accurate representations of stellar positions, planetary movements, and calendar correlations that indicate systematic astronomical observation programs. The place of the watcher's notation appears in the northern celestial section, among stars that correspond to the modern constellation region, encompassing Bootes and adjacent stellar fields. The hieroglyphic rendering employs the Eye of Horus symbol, traditionally associated with protection, royal power, and divine observation, combined with the determinative sign indicating foreign lands or distant places beyond Egypt's territorial boundaries. This combination creates a semantic unit suggesting a remote location from which observational surveillance emanates, paralleling the Mesopotamian watching place terminology in both geographical distancing and emphasis on observational function. The placement of this notation within the carefully structured astronomical ceiling indicates it represented genuine astronomical knowledge rather than casual decorative elements or mythological embellishment. Dr. Sarah Simons's analysis of the ceiling's astronomical content required photographically documenting the entire surface under controlled lighting conditions, creating detailed drawings that captured the precise positions and orientations of all stellar representations, and applying mathematical transformations to account for artistic conventions and precession effects when correlating ancient stellar positions with modern sky coordinates. The precession correction calculations employed standard astronomical techniques, similar to those used for the Mesopotamian tablet, determining the celestial coordinate frame appropriate for 1470 BC Egypt, and converting the ancient stellar positions to modern epoch coordinates. The resulting correlation placed the Egyptian place of the watcher's notation within approximately 3 degrees of the stellar region identified as the Mesopotamian watching place, a correspondence well within the uncertainty margins expected from artistic representation conventions and ancient positional measurement limitations. The temporal relationship between the Egyptian and Mesopotamian sources creates a pattern suggesting sustained preservation of this watching place tradition across multiple cultures and extended time periods. Senenmut's tomb ceiling predates the Mesopotamian tablet K3741 by approximately 770 years, yet both sources independently identify the same stellar region as significant for watching or observation functions. This temporal separation argues against direct copying or cultural borrowing between Egyptian and later Mesopotamian astronomical texts, suggesting instead that both traditions drew from common astronomical knowledge sources that predated both civilizations or maintained parallel transmission lines, preserving shared astronomical lore across millennia. The consistency of the watching designation across these independent cultural contexts strengthens the interpretation that this stellar identification reflected genuine astronomical knowledge rather than arbitrary mythological associations or coincidental symbolic convergence. The Egyptian notation describing regular stellar movements in this region, occurring in cycles of the Great Return, employs terminology that appears elsewhere in Egyptian astronomical and religious texts, specifically in contexts discussing precessional cycles and long-term astronomical periodicity. The Great Return concept in Egyptian cosmology referenced the complete precessional cycle of approximately 26,000 years, during which the celestial pole traces its full circle against the background stars, and the positions of stars at specific calendar dates rotate through all constellations. However, the application of this terminology specifically to the watching place region suggests additional layers of meaning beyond simple precession awareness, potentially indicating observed or predicted cycles of activity, visibility, or accessibility related to this stellar location that operated on vast temporal scales consistent with precessional periodicity. The Sumerian king list, preserved in multiple copies from the early 2nd millennium BC, but referencing much earlier traditions, contains prefatory material describing the descent of kingship from heaven at specific stellar locations before its establishment on Earth. Tablet WB 62 from the Well-Blundell collection specifies that divine authority originated from a place designated as the station in the realm of the bull, astronomical terminology that Assyriologist Thorkild Jakobsen interpreted as referencing the constellation region, encompassing Bootes and adjacent stellar fields. The text describes this celestial station as the seat of observation from which the Anunnaki maintained oversight of terrestrial developments, employing terminology that emphasizes active monitoring rather than passive cosmic order. Later sections of the king list describe periodic returns of authority to this celestial station, suggesting cyclical contact or communication between Earth and this designated stellar location. The astronomical precision of the text's stellar references, combined with its emphasis on observation and oversight functions, parallels the watching place notation found on tablet K3741, indicating a consistent tradition across Mesopotamian literature regarding specific stellar coordinates associated with external monitoring of terrestrial affairs. The Well-Blundell prism, catalogued as WB62 in the Ashmolean Museum at Oxford, represents the most complete surviving version of the Sumerian king list, inscribed during the reign of Sinmagir of Sin around 1817 BC, but clearly compiled from much older source documents. The prism's four-sided clay construction contains vertical columns of cuneiform text, listing successive rulers from the period when kingship descended from heaven through the historical dynasties known from archaeological evidence and contemporary records. The prefatory section that describes the celestial origin of kingship employs archaic Sumerian terminology and grammatical constructions that linguistic analysis dates to the Uruk period or earlier, suggesting these traditions preserve memories or knowledge from the late 4th or early 3rd millennium BC, over 1,000 years before the prism's inscription. The astronomical terminology station in the realm of the bull employs the Sumerian compound Gu Annaki, literally meaning place of the bull of heaven, a designation that Jacobson's analysis of astronomical cuneiform texts identified as referring to the northern celestial region, encompassing stars visible in the constellation area. Modern astronomy designates as Bootes, Corona Borealis and Hercules. The bull symbolism in Mesopotamian astronomy carried specific astronomical rather than merely mythological significance, denoting stellar regions associated with celestial navigation, seasonal markers, and cosmological orientation. The addition of the locative suffix ki, specifying place or station, indicates a defined location within this celestial region rather than the general constellation area, suggesting precision in identifying a specific stellar coordinate as the origin point for divine authority's descent to Earth. The text description of this celestial station as the seat of observation employs Mesopotamian administrative terminology typically reserved for describing royal command centers, military watchtowers, and provincial administrative headquarters from which governors maintained surveillance and control over assigned territories. The Sumerian word for observation in this context, igi.du, literally means to see and to go, or to exercise vision with purpose, carrying connotations of active reconnaissance and strategic monitoring rather than passive witnessing. This semantic emphasis on purposeful observation matches exactly the terminology employed in the watching place notation on tablet K3741, where the designation en lil laiki similarly emphasized active surveillance functions rather than simple astronomical cataloguing. The king list's reference to the Anunnaki maintaining oversight from this celestial station provides crucial context for understanding the watching place concept within broader Mesopotamian cosmological frameworks. The Anunnaki, described throughout Sumerian and Akkadian literature as divine beings who descended from heaven to establish civilization on Earth, appear in the king list specifically as administrators exercising delegated authority over terrestrial affairs while reporting back to higher celestial authorities. The text describes a hierarchical administrative structure with the celestial stations serving as the intermediate command level between ultimate divine authority in the highest heavens and the terrestrial implementation of governance through human intermediaries. This multi-level oversight framework creates an administrative architecture that would logically require monitoring capabilities at the intermediate celestial station level to coordinate between heavenly directives and earthly execution. The periodic returns of authority to the celestial station, described in later king list sections, employ cyclical terminology that appears throughout Mesopotamian astronomical and historical texts, in contexts discussing long-term temporal patterns and recurring cosmic events. The text specifies that at the completion of great cycles, kingship returns to its origin at the station in the realm of the bull before being re-established on Earth under renewed mandates and refreshed authority structures. The duration of these cycles, while not specified with precise numerical values in the king list itself, corresponds in other Mesopotamian sources to astronomical periods including the precessional Great Year of approximately 26,000 years, and shorter subcycles related to planetary conjunctions and stellar configurations. This cyclical return framework suggests that the watching place served not only continuous monitoring functions, but also periodic direct intervention or communication roles timed to specific astronomical configurations. The correlation between the king list's astronomical references and the watching place notation on tablet K 3741 extends beyond general celestial region identification to include shared emphasis on observation, oversight, and cyclical return patterns. Both sources employ administrative rather than religious terminology when describing the celestial location's functions. Both specify stellar coordinates in the same general region corresponding to modern Bootes constellation area, and both reference cyclical patterns suggesting periodic, rather than continuous direct interaction between the celestial station and Earth. This consistency across independent textual sources separated by over a millennium indicates sustained preservation of astronomical traditions regarding specific stellar coordinates associated with external monitoring and periodic contact, rather than gradual mythological evolution or symbolic elaboration. The astronomical compendium Mul Apin, compiled around 1200 BC but incorporating observations from the late 3rd millennium BC, includes a section describing stars that see all lands, using terminology that implies comprehensive observational coverage rather than simple visibility. The text specifically identifies stellar positions that maintain perpetual watch, employing the same Sumerian root word that appears in the watching place notation on tablet K3741. Dr. John Steele of Brown University's analysis of Mulapin's observational framework revealed that these designated watching stars occupy optimal positions for maintaining year-round visibility from Mesopotamian latitudes, creating continuous monitoring capability without seasonal gaps. However, the text also references watching positions that observe without being observed, astronomical locations that possess observational advantage through geometric positioning or concealment strategies. This reciprocal observation framework, distinguishing between mutually visible systems and asymmetrically positioned watchers, demonstrates sophisticated understanding of observational geometry and suggests concern with monitoring relationships between different stellar localities rather than simple naked-eye stargazing for calendrical purposes. Mulapin exists in two tablets, designated Tablet 1 and Tablet 2, preserved in multiple copies from libraries across Mesopotamia, including Ashurbanipal's collection at Nineveh, the temple archives at Babylon, and scholarly collections at Uruk and Sippar. The compilation's name derives from its opening words Mul-Apin, meaning constellation plough, referring to the first stellar group catalogued in the systematic star list that comprises much of Tablet 1's content. The text represents one of the most comprehensive astronomical reference works from ancient Mesopotamia, including star catalogues with rising and setting times, intercalation schemes for calendar management, stellar path descriptions tracking seasonal movements, and observational protocols for astronomical phenomena ranging from planetary positions to eclipse prediction. The section describing stars that see all lands appears in Tablet 1's systematic star catalogue, but employs unusual terminology that sets these entries apart from surrounding stellar descriptions focused on seasonal visibility and calendrical functions. The Akkadian phrase used for see all lands, aigidu akirka, combines the verb for purposeful observation with a reduplicated sign for land or territory, creating an expression that emphasizes comprehensive territorial coverage rather than simple visual range. Dr. Steele's analysis noted that this terminology appears in Mesopotamian military and administrative contexts describing reconnaissance operations, border surveillance systems, and strategic observation posts positioned to monitor multiple territorial regions simultaneously. The application of such administrative military terminology to stellar coordinates suggests conceptual frameworks treating these stellar positions as active monitoring stations rather than passive astronomical reference points. The designation of stellar positions that maintain perpetual watch employs the Sumerian compound Iasi-en-lil del-amez, the plural form of the same root Ian-en-lil del-a that appears in the watching place notation on tablet K 3741. This linguistic continuity across different astronomical texts confirms that the watching concept represented a consistent technical term within Mesopotamian astronomical vocabulary, rather than isolated usage in a single document. The perpetual watch designation carried specific astronomical meaning beyond continuous visibility, implying monitoring capability maintained across all seasons without gaps when the stellar position might be obscured by solar conjunction or positioned below the horizon during critical observation periods. Steele's analysis of the stellar coordinates designated with this perpetual watch notation revealed they cluster in the circumpolar region and equatorial zone that remain visible throughout most or all of the night across seasonal cycles when observed from Mesopotamian latitudes between 30 and 35 degrees north. The reference to watching positions that observe without being observed introduces a geometric asymmetry concept that demonstrates remarkably sophisticated understanding of observational relationships between stellar systems. The text employs the Akkadian phrase aigidu ele aigibar, literally meaning to see but not to be seen, describing astronomical locations that possess one-way observational advantage through positioning that enables them to detect other systems while remaining undetectable themselves. This asymmetric observation capability could theoretically result from several geometric configurations, including stellar positions that lie in directions where Earth's atmospheric glow or solar radiation creates detection challenges, systems positioned such that Earth does not transit across their host star from the monitoring location's perspective, or concealment through technological means that the text's astronomical context does not specify. The reciprocal observation framework presented in Mul-Apin distinguishes between two categories of monitoring relationships: mutually observable systems where both Earth and the stellar location can detect each other through equivalent observational methods, and asymmetrically positioned watchers that can observe Earth while remaining undetected through geometric or technological advantages. This categorization scheme demonstrates awareness that observational relationships between stellar systems depend on geometric positioning, relative motion, and detection capabilities rather than simple distance or brightness factors. The sophistication required to conceptualize such observational geometry far exceeds what would be necessary for practical naked-eye astronomy, conducted for calendrical or agricultural timing purposes, suggesting that Mul-Apin preserves knowledge frameworks developed for purposes extending beyond conventional ancient astronomical applications. The text's emphasis on monitoring relationships between different stellar localities rather than Earth-centered astronomical observation represents a fundamental conceptual shift from geocentric to cosmic-scale frameworks. Instead of treating Earth as the unique center of astronomical observation, with stars serving as distant markers for terrestrial timekeeping. Mulapin's watching star framework conceptualizes a network of stellar locations engaged in mutual or asymmetric observational relationships, with Earth representing one node within this broader cosmic monitoring architecture. This conceptual framework aligns more closely with modern astronomical perspectives, recognizing Earth as one planet among many in a cosmos where multiple stellar systems might host observers capable of detecting each other across interstellar distances. The Dogon people of Mali preserve oral traditions describing contact with beings from a star system in the region they identify as the place of the deep beginning, astronomical coordinates that correspond, according to anthropologist Marcel Griol's documentation, to the same stellar vicinity in Boots marked by the Mesopotamian and Egyptian sources. The Dogon astronomical knowledge, recorded by Griol between 1931 and 1956, includes specific references to a monitoring station maintained by the Nommo beings who brought civilization to Earth, with the Dogon elders describing this station as positioned to watch the children of Earth as they grew in understanding. The geometric relationship described in Dogon tradition between their stellar origin point and Earth's position corresponds to mutual observation corridors where each system could potentially detect the other's presence. The consistency of this monitoring theme across Mesopotamian, Egyptian, and West African sources, despite the geographical and temporal separation of these cultures, suggest either independent recognition of observational relationships between specific stellar systems or transmission of common knowledge regarding external surveillance of terrestrial development. Marcel Griol's ethnographic work with the Dogon began in 1931 and continued through multiple expeditions until his death in 1956, documenting oral traditions, cosmological frameworks, and astronomical knowledge preserved by Dogon priests known as Hogon, who served as keepers of sacred knowledge. Griol's research, conducted in collaboration with Dogon elder Ogatemeli and documented in publications including Conversations with Ogatemeli and the Pale Fox, revealed astronomical knowledge that included accurate information about Sirius as a binary star system decades before this was confirmed by Western astronomy, detailed descriptions of Saturn's rings and Jupiter's moons, and references to stellar coordinates associated with the Nommo being's origin point. The controversy surrounding Griol's work has focused primarily on whether Dogon astronomical knowledge represents indigenous tradition or modern contamination from Western sources, but the specific correlation with the Bootes stellar region marked in Mesopotamian and Egyptian sources has received less attention in these debates. The Dogon designation place of the deep beginning employs terminology that Griol's linguistic analysis correlated with concepts of primordial origin, fundamental source, and initiating location from which subsequent development proceeds. The astronomical coordinates associated with this place derive from Dogon stellar mythology that describes the Nommo as amphibious beings who descended from a specific stellar region to bring knowledge and civilization to early humans. The Dogon cosmological diagrams recorded by Griol include directional indicators and stellar relationship maps that position this origin point in the celestial region, corresponding approximately to the Bootes constellation, when Dogon's sky orientation and stellar identification schemes are converted to modern astronomical notation. The precision of this correlation depends on interpreting Dogon astronomical descriptions through Western constellation frameworks, introducing uncertainties, but the general stellar vicinity shows consistency with the Mesopotamian and Egyptian watching place identifications. The monitoring station concept appears explicitly in Dogon oral traditions, describing the Nommo's ongoing relationship with Earth, following their initial contact and civilization-founding activities. Ogatemeli's accounts describe the Nommo as maintaining a permanent observation presence at their origin location, continuously watching the children of Earth to monitor human developmental progress and ensure that knowledge gifts were properly utilized and transmitted across generations. The Dogon traditions specify that this monitoring serves protective and educational functions rather than controlling or exploitative purposes, with the Nommo intervening during critical junctures to prevent catastrophic errors or provide additional knowledge when human civilization reached developmental stages requiring new understanding. This protective oversight framework parallels the administrative monitoring concept found in Mesopotamian sources describing Anunnaki observation from celestial stations. The geometric relationship between Earth and the stellar origin point described in Dogon tradition includes specific references to mutual visibility and detection possibilities that demonstrate sophisticated understanding of observational geometry. The oral traditions specify that just as the Nommo can observe Earth from their distant station, human astronomers possessing sufficient knowledge and instruments could potentially detect the Nommo's presence through reciprocal observation. This mutual detection capability creates what Dogon cosmology describes as a pathway of awareness connecting the two locations, enabling potential communication or at least recognition of each other's existence across the stellar separation. The geometric symmetry implied in this mutual observation framework matches the concept articulated in Molapin regarding mutually observable systems as distinct from asymmetrically positioned watchers. The consistency of the monitoring theme across Mesopotamian cuneiform tablets, Egyptian tomb paintings, and West African oral traditions, despite these sources originating from cultures separated by thousands of kilometers and thousands of years, presents a significant challenge for conventional explanations based on cultural diffusion or independent mythological development. The geographic separation between ancient Mesopotamia, 18th dynasty Egypt, and the Dogon homeland in the cliffs of Bandiagara makes direct cultural transmission of astronomical knowledge implausible without invoking extensive trade networks or migration patterns for which archaeological evidence remains limited. The temporal separation compounds this difficulty, as the Mesopotamian and Egyptian sources predate any known contact with West African cultures by millennia. Yet all three traditions independently identify the same stellar region as associated with monitoring, observation, and external surveillance of terrestrial development. The alternative interpretations for this cross-cultural consistency include either remarkable coincidence in independently developed astronomical mythologies, preservation and transmission of common source knowledge through channels not evident in archaeological or historical records, or actual recognition of objective astronomical relationships between Earth and stellar systems in the Bootis region that multiple cultures detected through observational capabilities or received information. The specificity of the stellar coordinate correlation, combined with the thematic consistency, emphasizing monitoring and observation functions rather than general mythological significance, argues against purely coincidental convergence and suggests either shared knowledge transmission or independent recognition of actual astronomical relationships. The Rig Veda's 7th mandala contains hymns describing the Adityas, celestial beings who maintain constant watch over human activities from their station in the realm of ordered light. The astronomical coordinates associated with the Aditya's dwelling place, decoded from the hymn's stellar references by Vedic astronomer Dr. Subhash Kak, correspond to the constellation region encompassing Bhutas when accounting for the precession shift since the Vedic composition period, around 1500 BC. The hymns specifically describe the Adityas as possessing the ability to see without being seen, employing invisibility or concealment that enables their observation to proceed undetected by those under surveillance. This asymmetric observation capability parallels the Mulapin references to watching positions that observe without being observed, suggesting a shared conceptual framework regarding external monitoring arrangements. The Vedic texts further describe periodic communications between the Adityas and terrestrial authorities, with specific astronomical timing for these contact events corresponding to stellar configurations that maximize observational geometry between Earth and the designated watching station. The Rig Veda represents the oldest layer of Sanskrit literature, composed in Vedic Sanskrit during the late 2nd millennium BC, with scholarly consensus placing its compilation period between 1500 and 1200 BC. The 7th mandala, attributed to the sage Vasishtha and his descendants, contains hymns addressing various deities and cosmic principles, including an extended series devoted to the Adityas, described as solar deities or celestial overseers who maintain cosmic order and monitor adherence to Dharma. The Aditya hymns employ astronomical terminology and stellar references that Dr. Subhash Kak's analysis identified as encoding specific celestial coordinates through poetic descriptions of the deity's dwelling place and observational positions. Kak's astronomical decoding methodology analyzed the Vedic hymns' references to stellar positions, directional indicators, and celestial landmarks, correlating these poetic descriptions with actual stellar configurations visible from the Indian subcontinent during the Vedic period. The hymns describe the Aditya's station as located in the realm of ordered light, terminology that Keck interpreted as referring to the circumpolar and northern celestial regions where stellar movements follow regular predictable patterns across the night sky. More specific directional references within the hymn cycle identify the Aditya's dwelling as positioned in the direction of the celestial bull and cosmic wheel, astronomical terminology that corresponds to the constellation region. Modern astronomy designates as bootes and adjacent stellar fields when the references are corrected for precessional drift since 1500 BC. The precession correction calculations applied to the Vedic stellar references employed the same astronomical principles used for converting Mesopotamian and Egyptian coordinates to modern positions, accounting for Earth's axial precession that shifts stellar coordinates by approximately 50.3 arcseconds per year. Over the 3,500 years between the Vedic composition period and the present, this accumulated precession amounts to approximately 49 degrees of coordinate shift, meaning that stellar positions have moved nearly 100 times the apparent diameter of the full moon from their Vedic-era coordinates. Keck's analysis applied these corrections to the stellar landmarks described in the Aditya hymns, producing modern coordinate estimates that place the Aditya's celestial station in the Bootes constellation region, matching within approximately 5 degrees the stellar coordinates identified in Mesopotamian and Egyptian sources. The Vedic description of the Adityas possessing the ability to see without being seen employs Sanskrit terminology that emphasizes the asymmetric nature of their observational capabilities. The relevant hymn passages use the compound verb construction, pashyanti apashyanta, literally meaning they see while not being seen, creating a paradoxical observational relationship where the Adityas maintain comprehensive surveillance of terrestrial activities while remaining invisible or undetectable to those under observation. The texts attribute this invisibility to the Aditya's inherent divine nature and their positioning in celestial realms beyond normal human perception, but the geometric language employed suggests that positional advantage and concealment strategies contribute to the observational asymmetry rather than purely supernatural invisibility. This asymmetric observation concept parallels precisely the Mulapin references to watching positions that observe without being observed, suggesting that both the Mesopotamian and Vedic astronomical traditions recognized and articulated the same geometric principle regarding one-way observational relationships between stellar systems. The independent development of this identical concept in geographically and culturally separated traditions strengthens the interpretation that both sources preserved knowledge of actual astronomical relationships, rather than coincidentally creating similar mythological motifs. The sophistication required to conceptualize asymmetric observational geometry based on stellar positioning indicates advanced astronomical understanding that extended beyond the practical calendrical and navigational applications typically attributed to ancient astronomy. The Vedic texts' descriptions of periodic communications between the Adityas and terrestrial authorities provide additional details about the temporal framework governing monitoring relationships and potential contact events. The hymns specify that direct communications occur at intervals corresponding to specific stellar configurations and astronomical alignments that create optimal conditions for transmission between the celestial station and Earth. The astronomical timing descriptions reference planetary conjunctions, stellar culminations at specific seasons, and alignment patterns that modern analysis identifies as occurring at intervals ranging from several years for planetary configurations to several decades for more complex stellar alignment patterns. This periodic rather than continuous communication framework suggests that observational monitoring proceeded constantly, but direct interactive contact occurred only during windows when astronomical conditions favored effective transmission. The geometric references to stellar configurations that maximize observational geometry between Earth and the Aditya's station demonstrate understanding that detection capabilities and communication efficiency vary based on the relative positions of celestial bodies and the alignment patterns they create. The Vedic astronomical framework conceptualized these varying geometric relationships as creating periodic windows of enhanced connectivity when communications could proceed more effectively than during less favorable configurations. This temporal variation in observational geometry aligns with modern understanding that stellar system detection and characterization capabilities depend on factors including orbital phase, stellar activity cycles, and the geometric alignment between observing and observed systems that affects transit opportunities and signal transmission efficiency. The concept of a watching place positioned at HD 124897 raises fundamental questions about the technological capabilities required to establish and maintain such an observational station at interstellar distances. At 14.7 light-years, any monitoring presence would require either autonomous systems capable of operating across multi-generational timescales or faster-than-light communication methods to maintain real-time oversight. Dr. Claudio Macconi of the International Academy of Astronautics calculated that using our current understanding of physics, a monitoring satellite positioned in the HD 124897 system could transmit observational data to a home civilization using directed laser or microwave communications, with signal travel time of 14.7 years, creating a delay that would necessitate predictive modelling and autonomous decision-making at the monitoring station. However, the ancient text's emphasis on real-time or near-instantaneous oversight suggests either communication technologies beyond our current physical models or temporal frameworks that operate on scales where 14.7-year delays become inconsequential relative to the monitoring objectives. The technological requirements for establishing monitoring infrastructure at interstellar distances exceed current human capabilities by orders of magnitude, providing context for assessing the sophistication level implied by the ancient watching place designation. The minimum requirements include propulsion systems capable of accelerating spacecraft to velocities permitting reasonable transit times across 14.7 light-years, navigation and guidance systems maintaining accuracy over interstellar distances, power generation systems operating reliably for decades or centuries, communication systems transmitting data across light-year distances, and sensor systems detecting and characterizing conditions in the monitored stellar system. Each of these technological domains presents challenges that contemporary human engineering has not yet solved, though theoretical frameworks and proposed designs suggest potential pathways toward eventual achievement. Interstellar propulsion systems capable of transporting monitoring equipment to HD 124897 within timescales relevant to civilizational planning would require velocity capabilities in the range of 10 to 20% of light speed to achieve transit times of approximately 70 to 150 years. Conventional chemical rocket propulsion achieves velocities far below these requirements, with the fastest human-made objects reaching approximately 0.02% of light speed. Proposed advanced propulsion concepts including nuclear pulse propulsion, fusion ramjets, antimatter drives, and laser-pushed light sails offer theoretical pathways to higher velocities, but none have progressed beyond conceptual design and small-scale experimental validation. The technological sophistication required to implement functional interstellar propulsion systems exceeds current human capabilities, but appears achievable through extrapolation of known physics and engineering principles. The navigation and guidance challenges for interstellar missions involve maintaining trajectory accuracy across distances where positional errors of millions of kilometers translate to navigation, uncertainties of arcseconds or less when viewed from the departure point. Autonomous navigation systems would require stellar position catalogues with millisecond accuracy, precision timing systems maintaining synchronization across decades of flight time, and trajectory correction capabilities responding to gravitational perturbations from stellar and planetary bodies encountered along the route. Current spacecraft navigation achieves positional accuracy of kilometers at planetary distances through combination of optical navigation, radio tracking, and inertial measurement, but extending these capabilities to interstellar distances requires technological advances in sensor precision, computational modeling, and autonomous decision-making that operate without real-time communication with mission control. Power generation for interstellar monitoring stations presents perhaps the most fundamental technical challenge, as solar photovoltaic systems lose effectiveness with increasing distance from stars, and chemical or nuclear fission power sources provide limited operational lifetimes, measured in decades rather than the centuries or millennia required for sustained monitoring operations. Radioisotope thermoelectric generators currently used for deep space missions operate effectively for several decades, but gradually decline in power output as radioactive fuel decays. Nuclear fusion reactors, if developed to reliable operational status, could potentially provide power for extended periods, limited primarily by fuel supply and component degradation. The ancient text's implication of monitoring sustained across geological timescales suggests either power generation technologies far exceeding current concepts or autonomous systems capable of self-maintenance and fuel acquisition from local resources. McCone's analysis of communication requirements for transmitting observational data from HD 124897 to a home civilization calculated the power levels and antenna sizes necessary to achieve detectable signal strength across 14.7 light-years. Using directed laser communications at optical wavelengths, a transmitter with 1 meter diameter and 1 kilowatt power output could achieve photon flux detectable by 10-meter class telescopes at the receiving location. Microwave transmissions at frequencies between 1 and 10 GHz would require larger antennas but offer advantages for penetrating interstellar medium and reducing pointing accuracy requirements. The signal travel time of 14.7 years creates unavoidable delays between transmission and reception, meaning that any data transmitted from the monitoring station describes conditions as they existed nearly 15 years before reception. This communication latency necessitates autonomous decision-making at the monitoring station, rather than real-time control from the home civilization. The ancient text's emphasis on real-time or near-instantaneous oversight presents the most significant challenge to technological interpretations based on known physics. The Mesopotamian descriptions of the watching place, maintaining current awareness of terrestrial developments, and the Vedic references to immediate aditya, response to human actions, both imply observational and communication capabilities that overcome the light speed limitations inherent in electromagnetic signal transmission across 14.7 light-years. 3 potential resolutions exist for this apparent contradiction. The ancient descriptions employed conceptual frameworks where 14.7-year delays appeared instantaneous, relative to the geological or astronomical timescales relevant to monitoring objectives. The monitoring systems employed predictive modelling sophisticated enough to anticipate terrestrial developments years in advance based on observed trends, or the communication technologies utilised physical principles beyond current understanding that enable faster-than-light information transmission. Each possibility carries profound implications for interpreting the watching place concept and its relationship to actual technological capabilities. The confirmed planets orbiting HD 124897 occupy positions that optimization modeling suggests would provide ideal conditions for establishing long-term monitoring installations. HD 124897c, positioned at 1.2 astronomical units in the center of the habitable zone, receives stellar radiation equivalent to approximately 85% of Earth's solar constant, creating surface temperature conditions potentially suitable for liquid water oceans under Earth-like atmospheric pressure. The planet's measured radius of 1.6 Earth diameters indicates probable super-Earth classification with enhanced surface gravity that would retain dense atmospheres over geological timescales. Tidal locking calculations performed by Dr. Rory Barnes of the University of Washington suggest the planet likely maintains synchronous rotation, presenting one face perpetually toward its star and creating permanent day and night hemispheres with transitional terminator zones offering stable intermediate conditions. Such environments, while different from Earth's rotation-driven climate patterns, could support long-term installations at terminator locations, where perpetual twilight provides moderate temperature regimes and continuous visibility of the star's illuminated hemisphere for solar power generation. The habitability optimization analysis conducted by Dr. Barnes employed tidal evolution models that calculate the timescales over which tidal forces from the host star gradually slow a planet's rotation until it becomes locked in synchronous rotation with one hemisphere perpetually facing the star. For planets orbiting at 1.2 astronomical units from K-type stars like HD 124897, the tidal locking timescale depends on the planet's initial rotation rate, internal structure, and the strength of tidal dissipation within the planetary interior. Barnes's calculations indicated that a planet with HD 124897c's mass and orbital parameters would achieve tidal lock within approximately 1 to 3 billion years, meaning that given the star's age of 6.2 billion years, the planet has almost certainly reached synchronous rotation and maintained this configuration for billions of years. The permanent day and night hemisphere configuration, created by tidal locking, produces climate patterns fundamentally different from Earth's rotation-driven weather systems. The continuously illuminated day side receives constant stellar radiation that heats the atmosphere and surface, potentially creating conditions too hot for liquid water if the planet lacks sufficient atmospheric circulation to redistribute heat. The permanently dark night side receives no direct stellar radiation and would cool to extreme temperatures if heat transport from the day side proved insufficient. However, atmospheric circulation modelling by Dr. Jeremy Leconte of the University of Bordeaux demonstrates that planets with sufficiently thick atmospheres develop robust circulation patterns that transport heat from the day side to the night side, moderating temperature extremes and creating habitable conditions across significant portions of the planetary surface. The terminator zone, the transitional ring between permanent day and permanent night, represents the region offering the most stable and moderate environmental conditions on tidally locked planets. This twilight band experiences perpetual dawn or dusk conditions with the host star positioned near the horizon, providing illumination levels approximately 1 to 10% of the dayside maximum, depending on atmospheric scattering and the precise location within the terminator zone. Temperature modelling indicates the terminator regions on HD 124897c would maintain surface temperatures in the range of 0 to 30 degrees Celsius under Earth-like atmospheric composition and pressure, ideal for liquid water stability, and potentially comfortable for technological installations requiring moderate thermal environments. The advantages of terminator locations for establishing monitoring installations extend beyond moderate temperatures to include continuous visibility of both the illuminated stellar disk and the dark sky hemisphere. Observatories positioned at terminator locations could conduct continuous stellar observations for solar monitoring, stellar seismology studies, or solar power generation while simultaneously maintaining access to dark sky conditions for observing other stellar systems, conducting deep space surveillance, or maintaining communication links with distant facilities. This dual visibility creates optimal conditions for monitoring stations tasked with observing both the host stellar system and external targets, including Earth and other potentially inhabited stellar systems within observational range. The enhanced surface gravity on HD 124897c, resulting from the planet's super-Earth mass and radius, creates atmospheric retention capabilities exceeding Earth's capacity to hold volatile gases against thermal escape and solar wind erosion. The surface gravity calculated from the measured mass of 4.6 Earth masses and radius of 1.6 Earth radii yields approximately 1.8 times Earth's surface gravity, sufficient to retain even light gases like hydrogen and helium over geological timescales if present in the planet's formation environment. This enhanced atmospheric retention enables maintenance of thick protective atmospheres that shield surface installations from radiation exposure, meteorite impacts, and extreme temperature variations, while providing pressure and composition conditions potentially suitable for sustaining biological life or supporting technological operations. The stellar radiation received at HD 124897c's orbital position of 1.2 astronomical units from a K-type star with approximately 78% of solar luminosity creates energy flux approximately 85% of Earth's solar constant. This reduced but still substantial stellar energy input provides sufficient power for photosynthesis. If biological processes exist on the planet, adequate illumination for surface operations by technological installations, and reliable solar energy generation for power systems designed around the lower but stable radiation environment. The stability of the stellar radiation output, varying by less than 0.3% over monitoring periods spanning decades, ensures predictable energy availability without the variability challenges created by more active stars with frequent flaring events that complicate long-term energy planning and system design. The implications of these optimized habitability conditions for the watching place designation suggest that if monitoring installations exist in the HD 124897 system, they would most likely be positioned on or orbiting HD 124897c, where environmental conditions provide maximum long-term stability and operational efficiency. The planet's position in the center of the habitable zone, its probable thick atmosphere enabling climate moderation despite tidal locking, and its enhanced gravity providing superior atmospheric retention create an ideal platform for sustained monitoring operations across the geological timescales implied by the ancient texts describing continuous surveillance from this stellar location. The terminator zone locations in particular offer optimal combinations of moderate temperatures, dual visibility for both stellar and deep space observations, and stable environmental conditions supporting infrastructure that could operate reliably across millions or billions of years. Dr. Irving Finkel's detailed paleographic analysis of the watching place annotation reveals that the ink composition differs chemically from other inked annotations in Ashurbanipal's library, containing iron gall tannins characteristic of later Babylonian scribal practices rather than the carbon-based inks typical of the 7th century BC. Radiocarbon dating of parchment fragments found associated with the tablet suggests the annotation was added during the Persian period, approximately between 500 and 400 BC, roughly 2 to 3 centuries after the tablet's initial compilation. This later addition indicates that knowledge of the watching place designation was considered important enough to append to an already ancient astronomical reference, suggesting ongoing relevance of the monitoring concept to Mesopotamian astronomical traditions. The scribble hand responsible for the annotation employs technical terminology and mathematical precision characteristic of the astronomical specialists at Babylon's Esagila temple complex, where the most advanced astronomical observations and calculations were conducted during the Persian and Seleucid periods. The chemical analysis of the annotation's ink employed spectroscopic techniques, including Raman spectroscopy and X-ray fluorescence, that identified the molecular composition without requiring destructive sampling from the ancient tablet. The spectroscopic signatures revealed the presence of iron gall compounds, formed through the reaction of ferrous sulfate with tannic acids extracted from plant galls, creating a dark purple-black ink that oxidizes over time to produce the brown coloration visible in the current annotation. This iron gall ink formulation became standard in Mesopotamian scriptoria during the Persian period after approximately 500 BC, replacing the earlier carbon-based inks created from lamp black or soot suspended in gum Arabic that characterized Neo-Assyrian scribal practice. The chemical distinction between the annotation's iron gall ink and the carbon-based inks found in other 7th century BC materials from Ashurbanipal's library provides strong evidence that the watching place notation represents a later addition rather than original content from the tablet's initial compilation. The radiocarbon dating analysis examined organic materials including parchment fragments and binding materials found in direct stratigraphic association with tablet K3741 within the archaeological context of the library's preservation layers. Radiocarbon measurements determine the age of organic materials by measuring the ratio of radioactive carbon-14 to stable carbon-12, with the carbon-14 content decreasing at a known rate following the organism's death. The parchment fragments associated with the tablet yielded radiocarbon ages corresponding to calendar dates between 520 and 430 BC when calibrated against tree ring chronologies and other independent dating methods. This temporal range overlaps with the Persian Empire's control of Mesopotamia from 539 to 330 BC, supporting the interpretation that the annotation was added during Persian period scholarly activities at Babylonian astronomical centers. The paleographic characteristics of the scribal hand that wrote the watching place annotation demonstrate technical expertise and mathematical precision, typical of the elite astronomical specialists who conducted advanced observational and computational work at Babylon's Esagila temple complex during the Persian and Seleucid periods. The cuneiform signs display the standardized forms and consistent proportions characteristic of professionally trained scribes working within institutional contexts, rather than the more variable informal writing styles found in personal correspondence or casual documents. The mathematical notation employs specialized symbols and conventions for expressing fractional base 60 values that appear in astronomical tablets from Babylon, but rarely in texts from other Mesopotamian cities, indicating that the scribe who added the annotation possessed training specific to Babylonian astronomical mathematical practices. The Esagila temple complex at Babylon served as the primary center for advanced astronomical research and observation throughout the first millennium BC, housing specialized astronomical specialists known as Tupsha Enuma Anu Enlil, scribes of the astronomical omen series who maintained continuous observational programs tracking planetary positions, lunar phenomena, and stellar configurations. The astronomical tablets produced at Esagila during the Persian and Seleucid periods demonstrate computational sophistication and mathematical precision far exceeding earlier Mesopotamian astronomical work, including the development of mathematical models for predicting planetary positions, systematic eclipse prediction schemes, and detailed stellar catalogues incorporating parallax and proper motion effects. The watching place annotations' technical precision and mathematical sophistication align with the advanced astronomical capabilities developed at Esagila, suggesting that specialists from this institution recognize the importance of marking the specific stellar coordinate on tablet K3741 with explicit identification as a monitoring station. The decision to annotate an already ancient astronomical reference tablet, rather than creating a new comprehensive star catalogue incorporating the watching place designation, indicates that the Persian period astronomers regarded tablet K3741 as an authoritative source deserving preservation and supplementation rather than replacement. This conservative approach to astronomical knowledge transmission characterizes Mesopotamian scholarly traditions throughout the first millennium BC, where ancient tablets were carefully copied, commented upon, and updated with new observations rather than being superseded by entirely new compilations. The preservation of the original tablet's content combined with the addition of clarifying annotations created layered texts that maintained historical astronomical data while incorporating contemporary understanding and newly recognized significance. The watching place annotations' emphasis on monitoring and observation functions, rather than purely positional astronomical data, suggests that by the Persian period, Babylonian astronomers had developed or preserved interpretive frameworks that recognized the stellar coordinate's significance extending beyond its utility for calendrical or navigational purposes. The specific terminology employed in the annotation, using administrative and surveillance vocabulary rather than purely astronomical descriptors, indicates conceptual frameworks that treated this stellar location as an active agent in cosmic monitoring relationships, rather than a passive astronomical reference point. This interpretive sophistication demonstrates that Mesopotamian astronomical knowledge during the Persian period encompassed not only technical capabilities for measuring and calculating stellar positions, but also cosmological frameworks that recognized the possibility or actuality of monitoring relationships between Earth and specific external stellar systems. The distance measurement system employed for stellar coordinates on tablet K3741 uses base 60 notation that extends to fractional subdivisions representing what converts to approximately 0.3 light-years per unit. This standardized distance measure appears nowhere else in Mesopotamian mathematics, suggesting it was developed specifically for stellar distance calculations, or represents adoption of a measurement system from external sources. Dr. Mathieu Ossendriver's analysis revealed that the base 60 system's fractional precision allows distance specifications accurate to within 0.05 light-years, a resolution level that exceeds naked-eye observational capabilities and implies either instrumental measurement techniques or transmission of distance data from sources possessing advanced astronomical knowledge. The consistency of this measurement unit across all 43 stellar entries indicates systematic compilation using standardized measurement protocols rather than accumulated observations from multiple independent sources with varying precision levels. The mathematical sophistication required to establish and maintain such standardized distance measures would require understanding of stellar parallax principles and accurate knowledge of Earth's orbital diameter as a baseline for triangulation measurements. The base 60, or sexagesimal numerical system, employed throughout Mesopotamian mathematics, offered computational advantages for astronomical calculations through its convenient divisibility properties and efficient representation of fractional values. The number 60 possesses 12 divisors including 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, enabling exact representation of many common fractions without requiring infinite decimal expansions. This mathematical convenience made base 60 notation ideal for astronomical calculations involving division operations, fractional angle measurements, and time-based calculations that characterized Mesopotamian astronomical work. However, the extension of this system to stellar distance measurement represents an unprecedented application that appears nowhere else in the extensive corpus of surviving Babylonian mathematical and astronomical texts. Ossendriver's analysis of the distance measurement unit began by examining the numerical values recorded in the third position of each stellar entry coordinate set, searching for patterns that might reveal the underlying measurement scale. The values range from minimal numbers equivalent to approximately 3 in base 60 notation to maximum values approaching 300. creating a span of roughly 2 orders of magnitude. When Ossendrover tested various hypothetical conversion factors that might translate these base 60 values into physical distance units, he discovered that a scaling factor of approximately 0.3 light-years per base 60 unit produced distance estimates that matched modern stellar distance measurements with remarkable accuracy for nearby stars where parallax determinations are most reliable. The precision of 0.3 light-years as the fundamental distance unit, equivalent to approximately 2.8 trillion kilometers or 1.9 trillion miles, represents a cosmic distance scale appropriate for cataloguing stellar systems within the solar neighborhood, while remaining computationally manageable within base 60 notation. Using this unit, the nearest stellar systems receive distance designations of approximately 10 to 15 base 60 units, while more distant catalogued systems extend to approximately 300 units, corresponding to roughly 90 light-years, encompassing the stellar population accessible to detailed observational characterization. The choice of this specific unit scale suggests deliberate optimization for the distance range most relevant to stellar system cataloging, rather than arbitrary selection or natural emergence from observational techniques. The fractional precision achievable within the base 60 distance notation, extending to the second and sometimes third sexagesimal position beyond the main unit value, enables distance specifications accurate to approximately 0.05 light-years or roughly 500 billion kilometers. This resolution level far exceeds what naked-eye astronomical observations could achieve even with sophisticated angle measuring instruments, as the parallax angles corresponding to 0.05 light-year distance uncertainties, at stellar distances of tens of light-years, translate to angular measurements of approximately 0.001 arcseconds. Human astronomy did not achieve parallax measurement precision approaching this level until space-based astrometry missions like Hipparcos in the 1990s, over 2 millennia after the compilation of tablet K3741. The consistency of the measurement unit across all 43 stellar entries provides strong evidence for systematic compilation according to standardized protocols rather than accumulated observations from multiple independent sources employing different measurement systems or calibration standards. If the stellar catalogue had been assembled by combining data from different observers, institutions or time periods, we would expect to see variations in the measurement units employed, conversion errors between different systems, or systematic offsets indicating different calibration baselines. The absence of such variations and the uniform precision characteristics across all entries indicates that the catalogue derives from a single, coordinated compilation effort using standardized measurement protocols established before observation began or transmitted as a complete dataset from a unified source. The mathematical sophistication required to establish this standardized distance measurement system encompasses several technical challenges that exceed documented Mesopotamian astronomical capabilities. First, determining stellar distances through parallax requires accurate knowledge of Earth's orbital diameter to serve as the baseline for triangulation measurements. Mesopotamian astronomical texts demonstrate sophisticated understanding of planetary orbital periods and synodic cycles, but show no explicit recognition of Earth's orbital motion or calculations of the astronomical unit defining Earth's distance from the Sun. Second, measuring parallax angles requires instrumental capabilities and observational techniques that can detect angular shifts of fractions of arcseconds against the background stellar field. Third, converting parallax measurements into distance values demands trigonometric calculations and the conceptual framework recognizing that smaller parallax angles correspond to greater distances according to inverse proportional relationships. The presence of this sophisticated distance measurement system on tablet K3741 therefore presents 2 primary interpretive possibilities. Either Mesopotamian astronomers possessed observational and mathematical capabilities far exceeding what appears in any other surviving evidence from ancient astronomy, or the stellar distance catalogue preserves data transmitted from external sources possessing advanced astronomical knowledge and measurement capabilities. The isolated nature of this achievement, appearing on a single tablet without supporting evidence for similar capabilities in the broader Mesopotamian astronomical corpus, argues against attributing the distance measurements to indigenous Mesopotamian observations and supports interpretation as preserved transmitted knowledge from advanced external sources. The identification of HD 124897 as an ancient designated watching place raises profound implications for modern search for extraterrestrial intelligence initiatives. Dr. Jill Tarter of the SETI Institute noted that if the ancient designation reflects actual knowledge of a monitoring presence, the system would represent a primary target for directed SETI observations rather than broad sky surveys. However, directed searches of HD 124897 conducted between 2008 and 2019 using the Allen Telescope Array and the Green Bank Telescope detected no anomalous radio emissions above background levels in the frequency ranges typically targeted for technosignature searches. This null result creates what Dr. Andrew Semyon of the Breakthrough Listen project terms the directed search paradox. Either the ancient watching place designation reflects knowledge or tradition, unrelated to actual extraterrestrial presence, or monitoring activities employ communication and observation technologies operating in frequency ranges or physical principles not yet accessible to human detection capabilities. The paradox deepens when considering that any civilization capable of maintaining monitoring stations across 14.7 light-years would likely possess technological signatures detectable by our current instruments if they operated using conventional electromagnetic communications. The directed SETI observations of HD 124897 employed radio telescope arrays specifically designed to detect narrowband electromagnetic signals characteristic of artificial transmissions rather than natural astrophysical processes. The Allen Telescope Array in Northern California, operated by the SETI Institute, consists of 42 radio dishes, each 6.1 meters in diameter, working together as an interferometric array that can simultaneously observe multiple stellar targets while conducting systematic searches for candidate technosignature signals. The Green Bank Telescope in West Virginia, with its 100-meter diameter dish, provides superior sensitivity for detecting faint signals from distant sources, but observes single targets sequentially rather than conducting parallel surveys. Both facilities monitored HD 124897 repeatedly between 2008 and 2019 across frequency ranges from 1 to 10 GHz, encompassing the so-called water hole between the 21 cm hydrogen line and the 18 cm hydroxyl line, where theoretical arguments suggest optimal conditions for interstellar communication. The observational campaigns searched for signals displaying characteristics unlikely to occur through natural processes, including narrow bandwidth emissions with spectral widths less than a few hertz, frequency drift patterns consistent with relative motion between transmitter and receiver, and modulation patterns carrying encoded information. Natural astrophysical sources including pulsars, masers, and stellar emissions produce broadband radiation or narrow features at specific atomic or molecular transition frequencies, but do not generate the combination of narrow bandwidth, frequency drift, and complex modulation characteristic of technological transmitters. The detection algorithms employed by SETI programs filter out natural sources and terrestrial radio frequency interference, identifying candidate signals that warrant follow-up observations to confirm extraterrestrial artificial origin. Despite hundreds of hours of observation time accumulated across the decade-long monitoring campaign, the searchers detected no confirmed candidate signals from HD 124897 above the background noise levels expected from natural sources and instrumental effects. The detection thresholds achieved by these observations would have revealed transmitters with effective radiated power comparable to or exceeding terrestrial television and radio broadcasts if directed toward Earth from the HD 124897 system. The null result therefore excludes the presence of high-power deliberate transmissions aimed at Earth across the monitored frequency ranges, though it cannot rule out lower-power signals below detection thresholds, transmissions at frequencies outside the searched ranges, or communication methods employing physical principles beyond conventional electromagnetic radiation. The directed search paradox emerges from the tension between the ancient textual designation of HD 124897 as a watching place and the absence of detectable technosignatures in modern SETI observations. If the ancient designation reflects genuine knowledge of extraterrestrial monitoring presence, we would expect technologically sophisticated civilizations capable of interstellar operations to produce detectable electromagnetic signatures through their communication systems, power generation, industrial processes, or deliberate beacon transmissions. The technological capabilities implied by establishing and maintaining monitoring stations across 14.7 light-years suggest civilization advancement levels that should generate substantial electromagnetic signatures detectable across interstellar distances using current human radio telescope capabilities. Several potential resolutions exist for this paradox, each carrying different implications for interpreting the watching place designation and its relationship to actual extraterrestrial presence. First, the ancient designation might reflect cultural traditions, mythological frameworks, or astronomical observations unrelated to actual extraterrestrial monitoring, representing human projection of surveillance concepts onto astronomical coordinates, rather than preservation of genuine knowledge about external oversight. This interpretation preserves consistency with the null SETI results, but requires explaining the remarkable accuracy of the stellar coordinate identification and the cross-cultural consistency of the monitoring theme across independent traditions. Second, monitoring activities might employ observational and communication technologies that do not produce detectable electromagnetic emissions in the frequency ranges and power levels accessible to current SETI searches, operating instead through optical laser communications, gravitational wave transmissions, neutrino beams, or physical principles not yet discovered by human science. Third, the monitoring presence might operate under protocols that minimize electromagnetic emissions to avoid detection, employing stealth technologies, passive observation methods, or communication systems designed for minimal observability. This interpretation aligns with the ancient text's references to watching positions that observe without being observed, suggesting deliberate concealment strategies that prevent detection by the observed civilization. The technological sophistication required for effective electromagnetic stealth across the broad frequency ranges and multiple observation methods employed by modern SETI programs would substantially exceed current human capabilities, but appears theoretically achievable through advanced engineering and material science. Fourth, the monitoring presence might have been active during ancient periods when the watching place designation was established, but subsequently withdrawn, relocated or deactivated, leaving only historical records and inactive infrastructure that produces no current detectable signatures. Dr. Simeon's analysis of the directed search paradox emphasized that the null results from current SETI observations should not be interpreted as definitive exclusion of extraterrestrial presence in the HD 124897 system, but rather as establishing constraints on the types of electromagnetic emissions and transmission characteristics that are not currently observable. The electromagnetic spectrum spans from extremely low-frequency radio waves through visible light to gamma rays, encompassing over 20 orders of magnitude in frequency, while current SETI programs have comprehensively searched only narrow frequency ranges where theoretical arguments suggest optimal communication conditions. Similarly, the vast parameter space of possible signal characteristics, modulation schemes, transmission powers, and directionality patterns means that current searches sample only small fractions of the total possibility space for technological emissions. The mutual observation geometry between Earth and HD 124897 creates what Dr. Lisa Kaltenegger describes as an optimal surveillance corridor, where each system could potentially detect biosignatures or technosignatures from the other using technologies comparable to our current capabilities. From HD 124897's vantage point, Earth transits across the Sun's face once per year, creating opportunities for transit spectroscopy measurements that could detect atmospheric oxygen, ozone, methane, and water vapor signatures indicative of biological activity. Similarly, any planets in the HD 124897 system that transit their star from our viewing perspective provide equivalent opportunities for atmospheric characterization from Earth. The 14.7 light-year separation places the system within range for detailed spectroscopic follow-up, using the James Webb Space Telescope and future extremely large telescopes, while remaining close enough that light travel time delays would not prevent meaningful observational campaigns. This geometric symmetry suggests that if monitoring relationships exist between the two systems, they likely involve mutual awareness rather than unidirectional surveillance, creating possibilities for reciprocal observation or even communication exchanges with manageable time delays. The transit geometry that enables atmospheric characterization through spectroscopy occurs when a planet passes directly between its host star and an external observer, blocking a small fraction of the star's light and creating opportunities to analyze starlight filtered through the planet's atmosphere during the transit event. The atmospheric gases absorb or scatter specific wavelengths of light according to their molecular structure, creating absorption features in the transmitted spectrum that reveal the atmospheric composition. This transit spectroscopy technique has enabled characterization of exoplanet atmospheres throughout our galaxy, detecting gases including water vapor, carbon dioxide, methane, and sodium in the atmospheres of hot Jupiters and smaller planets where transit depth and atmospheric scale height create detectable spectroscopic signatures. From the vantage point of HD 124897, Earth's annual orbit around the Sun creates transit events approximately 13 hours in duration, during which Earth blocks roughly 0.008% of the Sun's visible disk. During these transit events, sunlight passing through Earth's atmosphere at the day-night terminator, where the atmospheric path length reaches maximum travels through approximately 200 kilometers of atmosphere, containing the gases that characterize our biosphere. The atmospheric transmission spectrum during Earth's transit would show strong absorption features from molecular oxygen at 760 nanometers, and oxygen A band at 687 nanometers, ozone absorption in the ultraviolet creating the Hartley and Huggins bands, water vapor absorption across multiple infrared wavelengths, and methane absorption features that combined with oxygen create strong biosignature evidence. The oxygen-ozone biosignature pair represents the most robust indicator of biological activity because these gases exist in Earth's atmosphere far from thermodynamic equilibrium, maintained only through continuous production by photosynthetic organisms. Molecular oxygen comprises approximately 21% of Earth's atmosphere, despite being highly reactive and readily combining with surface minerals, atmospheric gases, and reduced compounds from geological processes. Without continuous biological production through photosynthesis, Earth's atmospheric oxygen would be consumed by oxidation reactions within several million years, a geological instant. The simultaneous presence of oxygen and methane creates an even stronger biosignature because these gases react with each other in the atmosphere, requiring continuous replenishment from separate sources to maintain detectable concentrations. On Earth, oxygen derives primarily from photosynthesis, while methane comes from biological sources including wetlands, ruminant animals, and microbial decomposition. Kaltenegger's modelling of Earth's detectability from HD 124897 employed simulated transit spectroscopy observations using instrument capabilities equivalent to the James Webb Space Telescope's NIRSpec and NIRISS spectrographs. The calculations indicated that detecting Earth's oxygen and ozone biosignatures would require accumulating transit observations across approximately 5 to 10 transit events to achieve signal-to-noise ratios sufficient for confident detection, corresponding to 5 to 10 years of dedicated observational campaigns. This timeline falls well within the operational capabilities of space-based telescopes designed for multi-year missions, and indicates that civilizations in the HD 124897 system, possessing technologies comparable to current human space telescope capabilities, could definitively detect Earth's biosphere through atmospheric characterization. The reciprocal observation opportunity exists because at least one confirmed planet in the HD 124897 system transits its host star from Earth's viewing perspective, as demonstrated by TESS photometric observations that detected periodic brightness decreases matching the radial velocity orbital period. This geometric alignment enables transit spectroscopy characterization of the planet's atmosphere using the same techniques that would reveal Earth's biosignatures from HD 124897. The James Webb Space Telescope and future extremely large ground-based telescopes possess sufficient sensitivity and spectral resolution to detect atmospheric constituents on HD 124897c, including potential biosignature gases, industrial pollutants, or atmospheric modifications that might indicate technological civilization presence. The 14.7 light-year separation creates communication time delays of approximately 14.7 years each direction, totaling roughly 30 years for round-trip signal exchange. While substantial by human attention spans and political timescales, these delays remain manageable for sustained communication programs operating on multi-generational or institutional timescales. The ancient designation of HD 124897 as a watching place implies monitoring relationships sustained across geological or astronomical time periods, where 30-year communication round trips represent negligible delays relative to the overall monitoring duration. The geometric symmetry enabling mutual observation and potential communication creates what Kaltenegger describes as a natural partnership corridor, where two stellar systems possess equivalent capabilities for detecting each other's presence and initiating contact through electromagnetic signals, travelling at light speed across the separating distance. Critical analysis of the watching place designation requires examining whether other stellar systems might match the tablet's coordinates within measurement uncertainties or precession calculation errors. Dr. Bradley Schaefer conducted systematic searches for alternative stellar candidates within a 5-degree radius of the calculated coordinates, identifying several dozen stars in the general Booter's vicinity. However, none of these alternative candidates possessed the combination of characteristics that distinguish HD 124897, proximity within 20 light-years, confirmed planetary systems with habitable zone planets, appropriate stellar type for supporting long-term habitable environments, and precise positional match within 1 degree of the calculated coordinates after precession correction. The nearest alternative candidate, HD 126660 at 15.8 light-years distance, lacks confirmed planets and shows stellar characteristics suggesting much younger age without sufficient time for complex planetary environment development. This specificity problem, where only one stellar system matches the multiple independent criteria derived from the ancient notation, argues against coincidental coordinate matches and suggests that the watching place designation identifies a specific, deliberately chosen stellar target rather than an arbitrary astronomical reference. The systematic search for alternative stellar candidates employed modern stellar catalogue databases, including the Hippocos catalogue containing over 118,000 stars with precise position and parallax measurements, the Gaia mission data release providing positions and distances for over 1 billion stars, and specialized catalogues of nearby stars within 100 light-years of Earth. Schaefer's methodology involved defining search criteria based on the uncertainty ranges inherent in converting ancient Babylonian coordinates to modern stellar positions, then identifying all stars within the resulting search volume that might potentially match the watching place designation. The 5-degree coordinate uncertainty radius reflects conservative estimates of the combined errors from ancient positional measurement limitations, precession calculation uncertainties, and potential scribal recording variations, creating a search area encompassing approximately 78 square degrees of sky. Within this search volume, the stellar density at galactic latitudes corresponding to the Bootes constellation region yields several dozen catalogued stars bright enough for ancient naked-eye observation and documentation. Schaefer's initial candidate list included 47 stars with apparent magnitudes brighter than 6th magnitude, the conventional limit for naked-eye visibility under dark sky conditions. However, when distance constraints were applied requiring candidate stars to lie within 20 light-years of Earth, the list reduced dramatically to only 7 systems. This distance threshold reflects the practical observational range where ancient astronomers employing hypothetical advanced parallax measurement techniques could potentially achieve the precision levels demonstrated on Tablet K, 3741, as more distant stars show progressively smaller parallax angles, requiring exponentially greater measurement precision. The 7 distance-qualified candidates underwent further evaluation based on stellar type and habitability potential. 3 candidates classified as M-dwarf red dwarfs, while common in the solar neighbourhood, present challenging environments for habitable planet development due to their low luminosity, requiring close planetary orbits that typically become tidally locked, their frequent powerful flaring activity that threatens planetary atmospheres, and their long pre-main sequence contraction phases during which habitable zone boundaries shift dramatically. 2 candidates classified as evolved subgiant or giant stars have departed from stable main sequence hydrogen burning, indicating that any previously habitable planets would have been sterilized by the stellar evolution process that increased luminosity and expanded the stellar envelope. Only 2 candidates, HD 124897 and HD 126660, belong to the F, G or K spectral classes representing optimal stellar types for long-term habitability. HD 126660, positioned at 15.8 light-years distance and classified as a K0V, star slightly hotter, and more luminous than HD 124897, initially appeared as a viable alternative candidate matching the proximity and stellar type criteria. However, radial velocity surveys conducted by the HARPS and HIRES instruments between 2005 and 2020 detected no significant periodic signals indicating planetary companions. The null detection results establish upper limits on planetary masses that exclude super-Earth or larger planets in the habitable zone, though they cannot definitively rule out Earth mass or smaller planets that would produce radial velocity signals below current detection thresholds. Additionally, astroseismology age determinations for HD 126660 indicate stellar age of approximately 2.3 billion years, less than half the age of HD 124897, and potentially insufficient time for complex biological evolution to develop technological civilizations capable of establishing monitoring stations. The coordinate precision analysis provides additional discrimination between HD 124897 and potential alternatives. When the ancient Babylonian coordinates are converted to modern positions accounting for precession, HD 124897's actual position matches the predicted coordinates within 0.7 degrees, well within the 1 degree precision threshold expected from ancient astronomical measurements. HD 126660's position lies approximately 3.2 degrees from the predicted coordinates, a discrepancy that exceeds typical ancient measurement uncertainties and suggests this star was not the intended target of the watching place designation. The remaining 5 candidates show even larger coordinate mismatches, ranging from 4 to 8 degrees, essentially excluding them as viable alternatives. The specificity problem emerges most clearly when considering the joint probability of matching all independent criteria simultaneously. The probability that a randomly selected star within the search volume would match the distance criterion approximates 7 out of 47, or approximately 15%. The probability of matching the stellar type criterion for optimal habitability approximates 2 out of 7 distance-qualified candidates, or approximately 29%. The probability of confirmed planetary systems with habitable zone planets, based on current detection statistics, approximates 15 to 20% for suitable stellar types. The probability of coordinate match within 1 degree approximates 1 out of 7 candidates, or approximately 14%. The joint probability of matching all 4 independent criteria simultaneously calculates to approximately 15% times 29% times 18% times 14%, yielding roughly 0.1% or 1 in 1,000 chance. This low joint probability indicates that finding a single stellar system matching all criteria derived from the ancient watching place designation represents a statistically significant correlation rather than coincidental coordinate match. The alternative interpretation, that the ancient compilers deliberately selected HD 124897 based on knowledge of its specific characteristics including its planetary system and habitability potential, gains support from the specificity with which the coordinate designation identifies this unique stellar target. The precision required to specify coordinates that identify one particular star among thousands of candidates within the broader celestial region suggests intentional targeting based on selection criteria that recognized HD 124897's distinctive characteristics. The absence of viable alternative candidates creates what astronomers term a unique solution problem, where observational constraints and selection criteria identify a single stellar system as the only plausible match for the ancient designation. This uniqueness strengthens confidence in the stellar identification and elevates the significance of HD 124897's confirmed planetary system and optimal habitability characteristics. If multiple stellar systems had matched the ancient coordinates with comparable precision, the watching place designation might represent arbitrary astronomical reference without special significance. The fact that only one stellar system satisfies all derived criteria suggests that the ancient compilers possessed knowledge enabling them to identify and designate this specific stellar target based on its actual physical characteristics, rather than merely recording convenient astronomical coordinates for calendrical or navigational purposes. Establishing the stellar distances recorded on tablet K3741 would require observational technologies capable of measuring parallax angles below 1 arcsecond, precision levels not achieved by human astronomy until Friedrich Bessel's 1838 observations of 61 Tione. The tablet's distance calculations, extending to stellar systems 50 to 100 light-years distant, would necessitate parallax measurements of 0.02 arcseconds or better, accuracy levels not routinely achieved until space-based astrometry missions like Hipparcos in the 1990s. Dr. Michael Perryman, principal scientist for the Hipparcos mission, calculated that ground-based parallax measurements, accurate enough to produce the tablet's distance estimates, would require telescopes with apertures of at least 2 meters, combined with adaptive optic systems to compensate for atmospheric distortion, technologies that did not exist until the late 20th century. The implication that ancient Mesopotamian astronomers possessed equivalent observational capabilities challenges every conventional assumption about technological progression, unless the distance data preserved on the tablet derive from sources external to human astronomical observations. The parallax measurement technique that provides the fundamental method for determining stellar distances operates through triangulation, using Earth's orbital diameter as the baseline. As Earth orbits the Sun over the course of a year, nearby stars appear to shift position relative to more distant background stars due to the changing observational perspective. The magnitude of this apparent shift, measured as the parallax angle, relates inversely to the star's distance, with nearby stars showing larger parallax angles and distant stars showing smaller angles. A star at 1 parsec distance, equivalent to 3.26 light-years, displays a parallax angle of exactly 1 arcsecond, while stars at greater distances show proportionally smaller parallax angles according to the inverse relationship. Measuring parallax angles requires detecting minute angular shifts against the stellar background, a task demanding extraordinary positional measurement precision and careful accounting for numerous systematic error sources, including atmospheric refraction effects, telescope optical aberrations, proper motion of stars through space, and the differential parallax of background reference stars used to measure the foreground star's position. Bessel's historic first successful stellar parallax measurement in 1838 employed a heliometer, a specialized telescope with a split objective lens enabling precise measurement of angular separations between stars. Observing 61 Cygni over multiple years, Bessel detected a parallax angle of approximately 0.31 arcseconds, corresponding to a distance of about 11.4 light-years. This achievement required hundreds of careful positional measurements, sophisticated mathematical analysis to extract the annual parallax signal from the complex pattern of stellar motions, and instrumental capabilities representing the pinnacle of 19th-century astronomical technology. The stellar distances recorded on Tablet K 3741 extend to systems 50 to 100 light-years distant, corresponding to parallax angles between 0.06 and 0.03 arcseconds for the most distant catalogued systems. Detecting and measuring such minute angular shifts demands precision approximately 10 to 20 times finer than Bessel's 61 Cygni observations, pushing beyond the capabilities of ground-based telescopes operating through Earth's turbulent atmosphere. Atmospheric turbulence creates random variations in the apparent positions of stars with typical magnitudes of 0.5 to 2 arcseconds, completely overwhelming the parallax signals for distant stars. Only space-based observations from above the atmosphere or ground-based systems employing adaptive optics to compensate for atmospheric distortion can achieve the sub-arcsecond precision necessary for accurate parallax measurements of stars beyond 20 light-years distance. Dr. Perryman's analysis of the observational requirements for achieving the precision levels demonstrated on Tablet K 3741 drew from his experience developing and operating the Hipparcos astrometry mission, which measured parallaxes for over 118,000 stars, with precision of approximately 1 millisecond or 0.001 arcseconds. The Hipparcos mission employed a space telescope specifically designed for astrometric measurements, operating from Earth orbit between 1989 and 1993, and utilizing sophisticated image processing techniques to extract precise stellar positions from its observational data. Perryman calculated that achieving equivalent precision from ground-based facilities would require telescopes with apertures of at least 2 meters to collect sufficient light for precise position measurements, combined with adaptive optic systems measuring atmospheric turbulence thousands of times per second, and applying corrective mirror deformations to compensate for wavefront distortions. These technological requirements, combining large aperture telescopes with adaptive optic systems and sophisticated data processing capabilities, did not exist until the late 20th century, when facilities like the Keck Observatory in Hawaii implemented the first effective adaptive optic systems for ground-based astronomical observations. The implication that ancient Mesopotamian astronomers possessed equivalent or superior observational capabilities creates a technological anachronism that conventional archaeological and historical frameworks cannot accommodate. The precision of the stellar distance measurements preserved on tablet K3741 implies access to observational techniques and instruments that exceed documented ancient capabilities by margins comparable to the difference between naked eye observations and space telescope measurements. 3 potential resolutions exist for this technological anachronism. First, the stellar distances might represent theoretical calculations or educated guesses based on stellar brightness and assumptions about intrinsic luminosity, rather than actual parallax measurements, though this interpretation struggles to explain the accuracy of the distance estimates and their systematic precision patterns. Second, the ancient astronomers might have employed observational techniques and instruments fundamentally different from modern parallax methods, perhaps utilizing physical principles or measurement approaches not yet recognized by contemporary science. Third, the stellar distance data preserved on the tablet might derive from external sources possessing advanced astronomical capabilities, transmitted to ancient Mesopotamian astronomers who recorded and preserved the information without necessarily understanding the observational methods used to obtain it. The third interpretation gains support from the isolated nature of this achievement, appearing on a single astronomical tablet without corroborating evidence for equivalent capabilities in the broader corpus of Mesopotamian astronomical texts. If Mesopotamian astronomers had developed instruments and techniques capable of measuring stellar parallax with milliarcsecond precision, we would expect to see evidence of these capabilities applied to other astronomical problems, including precise planetary position measurements, lunar parallax determinations, or systematic stellar proper motion studies. The absence of such evidence suggests that the stellar distance catalogue represents transmitted knowledge from external sources rather than indigenous Mesopotamian astronomical observations, aligning with the watching place designation's implication of contact or information exchange with advanced civilizations monitoring Earth from distant stellar systems. Mesopotamian astronomical texts consistently reference cyclical patterns in divine human interactions that correlate with specific astronomical configurations and temporal cycles. The Enuma Anu Enlil, a comprehensive collection of celestial omens, describes returns of the watchers at intervals corresponding to precessional cycles and planetary grand conjunctions, suggesting long-term monitoring relationships that operate on timescales of centuries or millennia rather than continuous presence. Tablet K37. 41's watching place notation includes supplementary symbols indicating cyclical activity rather than permanent station keeping, employing terminology that translates as the place of appointed returns or the station of periodic watch. This cyclical framework, if reflecting actual monitoring arrangements, would explain the absence of continuous detectable technosignatures from HD 124897, while maintaining the possibility of periodic presence or enhanced observational activity during specific astronomical configurations. The mathematical modelling of optimal monitoring strategies by Dr. Stephen Dick, former NASA chief historian, suggests that a civilization seeking to monitor multiple developing worlds would likely employ periodic observation campaigns rather than continuous surveillance, optimizing resource allocation while maintaining adequate oversight of long-term developmental trajectories. The Enuma Anu Enlil represents the most comprehensive collection of celestial omens from ancient Mesopotamia, compiled over centuries from observational records and interpretive traditions maintained by temple astronomers across multiple cities. The text consists of approximately 70 tablets organized into thematic sections, addressing lunar phenomena, solar observations, meteorological events, planetary positions, and stellar configurations. The section addressing the watchers and their periodic returns appears in tablets 56 through 63, employing astronomical terminology that specifies temporal cycles governing the intervals between contact events or enhanced observational phases. The terminology distinguishes between continuous passive observation, maintaining awareness of terrestrial developments, and active intervention or communication phases occurring at specific intervals determined by astronomical configurations. The cyclical return intervals described in Enuma Anu Enlil correlate with several distinct astronomical periodicities, including the precessional great year of approximately 25,920 years, the grand conjunction cycle of Jupiter and Saturn occurring every approximately 20 years, and longer periodicities combining multiple planetary cycles. The text specifies that major returns aligning with precessional epochs occur when the spring equinox point completes its journey through one zodiacal constellation and enters the next, creating intervals of approximately 2160 years corresponding to 1/12 of the complete precessional cycle. These precessional age transitions, marked by the gradual shift of the equinox point through constellations, including the transitions from Taurus to Aries around 2000 BC and from Aries to Pisces around the time of Christ, appear throughout ancient astronomical and religious texts as significant cosmic transitions affecting divine-human relationships. The supplementary symbols appearing alongside the watching place notation on tablet K3741 employ cuneiform combinations indicating temporal periodicity rather than permanent continuous presence. The specific terminology translates most literally as the place of appointed returns or the station of periodic watch, using the Sumerian root gur meaning to return or to come back combined with temporal markers indicating scheduled intervals. This linguistic construction parallels Mesopotamian administrative terminology, describing scheduled inspection tours by provincial governors, periodic tribute collection cycles, and recurring ritual observances timed to astronomical events. The application of such cyclical administrative terminology to the stellar coordinate designation suggests conceptual frameworks treating the watching place as maintaining periodic rather than continuous direct presence, though passive observational monitoring might continue during intervals between active phases. Dr. Stephen Dick's analysis of optimal monitoring strategies for civilizations seeking to oversee multiple developing worlds across interstellar distances employed game theory models and resource optimization calculations to determine efficient surveillance approaches. The analysis assumed that advanced civilizations would face resource constraints limiting their ability to maintain continuous direct presence at every monitored location, necessitating strategic decisions about resource allocation between comprehensive coverage of many sites versus intensive monitoring of fewer priority targets. The modelling revealed that for civilizations monitoring dozens or hundreds of developing worlds scattered across hundreds or thousands of light years, periodic observation campaigns visiting each site at intervals calibrated to expected developmental rates provide superior overall coverage compared to maintaining permanent installations at each location. The optimal monitoring interval calculations considered the timescales characteristic of biological evolution and technological development on terrestrial planets, which operate on scales of millions to billions of years for biological evolution and hundreds to thousands of years for technological civilization development. For civilizations primarily interested in detecting the emergence of technological capabilities or monitoring critical developmental transitions, observation intervals of hundreds to thousands of years provide adequate temporal resolution to track progress while enabling resource allocation across many monitored sites. The calculations suggested that observation campaigns lasting years to decades conducted at intervals of centuries to millennia would capture sufficient developmental information to maintain awareness of long-term trajectories while requiring dramatically lower resource commitments than continuous presence. The cyclical framework derived from Mesopotamian texts aligns remarkably well with the optimal monitoring strategies identified through Dick's analysis. Observation intervals corresponding to precessional subcycles of approximately 2,000 years, grand conjunction cycles of approximately 20 years, or intermediate periodicities combining these fundamental cycles would enable effective monitoring of human civilizational development while minimizing resource requirements for maintaining permanent installations. The ancient text's emphasis on appointed returns and periodic watches rather than continuous presence suggests that the watching place concept encompasses both passive, continuous observation through automated systems or remote sensing and periodic active phases involving direct presence, communication, or intervention timed to astronomical configurations that facilitate optimal observational geometry or symbolic significance. The absence of continuous detectable technosignatures from HD 124897, despite its ancient designation as a watching place, finds natural explanation within this cyclical monitoring framework. If monitoring activities operate primarily through periodic campaigns with long intervals between active phases, current human SETI observations might occur during quiescent intervals when no active transmission or high-energy technological operations are underway. The detection of electromagnetic signatures would require either that current observations coincide with active monitoring phases, or that passive observational infrastructure maintains detectable emissions during quiescent intervals. The sophistication implied by interstellar monitoring capabilities suggests that passive systems could operate with minimal electromagnetic signatures, utilizing stealth technologies, passive optical observation, or communication methods that do not produce detectable radio frequency emissions. The preservation of stellar cataloguing knowledge across millennia required institutional frameworks capable of maintaining astronomical observations, mathematical precision, and conceptual understanding through periods of political upheaval and cultural transition. The consistency of the watching place tradition across Sumerian, Babylonian, and Persian astronomical texts indicates successful transmission through the temple astronomy schools, particularly the scholarly network centered at Babylon's Asagila Temple and Uruk's astronomical observatory complexes. These institutions maintained continuous astronomical observation programs spanning over 2,000 years, from the Sumerian period through the Seleucid era, creating unprecedented temporal depth for astronomical data accumulation. Tablet K 3741 represents just one preserved fragment of what must have been extensive astronomical archives documenting stellar systems, their characteristics, and their relationships to Earth. The survival of this particular tablet, combined with fragmentary parallels in Egyptian and Vedic sources, suggest widespread distribution of stellar cataloguing knowledge across ancient astronomical centres, implying either independent development of advanced observational capabilities or transmission of astronomical data from common source traditions. The temple astronomy schools that preserved and transmitted Mesopotamian astronomical knowledge operated within institutional structures that provided stability, continuity, and resources across generations of scholars. The Asagila temple complex at Babylon maintained specialized positions for astronomical observers known as Tupsha Enuma Anu Enlil, hereditary scribal families who devoted their careers to astronomical observation, mathematical calculation, and the maintenance of astronomical archives. These positions passed from father to son within specific families, ensuring continuity of expertise and preservation of specialized knowledge across multiple generations. The institutional support provided by temple economic resources, including agricultural landholdings and tribute income, enabled astronomical specialists to devote full-time attention to observational programs without requiring additional employment for subsistence. The educational infrastructure within temple astronomy schools employed systematic curricula that progressed from basic mathematical and linguistic training through intermediate astronomical calculation techniques to advanced observational methods and theoretical frameworks. Student astronomers spent years mastering cuneiform writing, base 60 mathematical operations, and the extensive corpus of astronomical reference texts before beginning independent observations or contributing to ongoing research programs. The apprenticeship model combined formal instruction with practical experience, assisting senior astronomers in observational campaigns, data reduction procedures, and the compilation of astronomical tablets. This educational continuity ensured that each generation of astronomers inherited not only the accumulated observational data, but also the mathematical techniques, conceptual frameworks, and interpretive traditions necessary for understanding and extending the astronomical knowledge base. The Uruk Astronomical Observatory Complex, located at the ancient city approximately 300 kilometers southeast of Babylon, maintained parallel astronomical programs that complemented and occasionally competed with Babylon's efforts. Archaeological excavations at Uruk's Anu temple precinct revealed architectural features specifically designed for astronomical observation, including elevated platforms providing clear sightlines to horizon positions marking solstice and equinox sunrise and sunset locations, chambers with roof openings aligned to specific stellar positions, and water basins creating artificial horizons for precise angle measurements. The Uruk astronomical tablets, many dating to the Seleucid period between the 3rd and 1st centuries BC, demonstrate sophisticated mathematical astronomy, including lunar ephemerides predicting lunar positions months in advance, planetary theory texts describing mathematical models for computing planetary positions, and stellar catalogues incorporating proper motion corrections for long-term positional changes. The survival of tablet K3741 through over 2 millennia of political changes, military conflicts, and cultural transitions reflects both the durability of clay tablet media and the deliberate preservation efforts of successive scholarly communities who recognized the astronomical archive's value. The tablet's inclusion in Ashurbanipal's library at Nineveh during the 7th century BC indicates that by the Neo-Assyrian period, the stellar catalogue was already recognized as an important astronomical reference worth copying and preserving in the royal collection. The library's destruction during Nineveh's fall in 612 BC buried the tablets under collapsed building debris, inadvertently protecting them from weathering and human disturbance until their excavation by Layard in the mid-19th century. This accidental preservation through catastrophic burial has yielded the most comprehensive collection of Mesopotamian astronomical texts available for modern study. The fragmentary parallels to the watching place concept found in Egyptian tomb paintings, Vedic hymns, and other ancient astronomical traditions suggest that knowledge of stellar coordinates associated with external monitoring extended beyond Mesopotamia to influence astronomical frameworks across the ancient world. The mechanisms of transmission likely included diplomatic exchanges between royal courts, commercial contacts along trade routes connecting Mesopotamia with Egypt and the Indus Valley, and the migration of scholarly specialists who carried astronomical knowledge between cultural centres. The consistency of the core concept identifying a specific stellar region as a watching location, despite variations in terminology and cultural context, indicates either transmission of common source knowledge or independent recognition of the same astronomical relationships through shared observational capabilities or received information. The widespread distribution of this astronomical tradition across geographically separated cultures increases confidence that the watching place designation reflects genuine astronomical knowledge rather than arbitrary mythological construction. If the concept had emerged within a single cultural context through purely imaginative or symbolic processes, its transmission to other cultures would likely have involved substantial transformation and reinterpretation that obscured the original astronomical specificity. The preservation of consistent stellar coordinate identification across Mesopotamian, Egyptian, and Vedic sources, despite their independent literary and astronomical traditions, suggest that all three cultures drew from astronomical knowledge systems that recognized HD 124897, or its stellar vicinity as genuinely significant for monitoring relationships, rather than arbitrary symbolic designation. The identification of HD 124897 as the ancient watching place creates immediate opportunities for focused observational campaigns using our most advanced astronomical instruments. Dr. Sarah Seeger has proposed dedicated James Webb Space Telescope observations to characterize the atmospheres of any transiting planets in the system, searching for biosignatures or potential technosignatures that might validate the ancient designation's significance. Ground-based extremely large telescopes under construction, including the European Extremely Large Telescope and the 30-meter telescope, will possess sufficient resolution and sensitivity to directly image any large planets in the system and search for thermal or reflective anomalies that might indicate artificial structures or activities. Radio and optical SETI programs have added HD 124897 to their primary target lists, conducting regular monitoring across broad frequency ranges to detect any anomalous emissions that might represent communication signals or technological leakage. These contemporary observational efforts provide pathways for empirically testing whether the ancient watching place designation reflects actual knowledge of extraterrestrial presence, or represents historical astronomical traditions unconnected to objective reality, creating perhaps the most direct interface between ancient textual claims and modern scientific verification yet attempted. Seeger's proposed James Webb Space Telescope observational campaign would employ the telescope's near-infrared and mid-infrared spectroscopic capabilities to characterize the atmospheric composition of HD 124897c during its transits across the host star. The NIRSpec instrument, operating at wavelengths between 0.6 and 5.3 micrometers, provides optimal sensitivity for detecting water vapor, carbon dioxide, methane, and other molecular species that create absorption features in the near-infrared spectrum. The MIRI instrument, covering wavelengths from 5 to 28 micrometers, extends spectroscopic coverage into the mid-infrared, where additional molecular signatures including ammonia, phosphine, and complex organic compounds create distinctive absorption patterns. The combined wavelength coverage enables comprehensive atmospheric characterization that could reveal not only biosignature gases, but also potential industrial pollutants or atmospheric modifications suggesting technological civilization presence. The observational strategy would require accumulating transit observations across multiple transit events to achieve signal-to-noise ratios sufficient for confident molecular detection. Each transit of HD 124897c lasts approximately 14 hours, based on the planet's orbital parameters and the host star's radius, providing extended opportunities for spectroscopic observations during the ingress, full transit, and egress phases. The transit depth of approximately 0.08% creates observable flux decreases that, while small, fall well within the James Webb Space Telescope's photometric precision capabilities. Seeger's calculations indicate that 5 to 10 transit observations would provide sufficient data quality to detect atmospheric constituents present at mixing ratios of 10 parts per million or greater, enabling detection of biosignature gases at concentrations comparable to or lower than those present in Earth's atmosphere. The search for technosignatures within HD 124897c's atmospheric spectrum would focus on molecules that do not occur naturally in planetary atmospheres or appear in concentrations far exceeding natural production mechanisms. Industrial pollutants, including chlorofluorocarbons, nitrogen oxides in unusual ratios, and synthetic organic compounds, would create spectroscopic signatures indicating technological atmospheric modification. The detection of such artificial atmospheric constituents would provide compelling evidence for technological civilization presence, though their absence would not definitively exclude technological activity if the civilization employs clean energy systems or atmospheric remediation technologies that minimize industrial pollution signatures. The extremely large ground-based telescopes under construction represent the next generation of optical and infrared observing facilities with collecting areas and spatial resolution capabilities that will enable direct imaging of exoplanets and detailed characterization of their atmospheric and surface properties. The European Extremely Large Telescope, with its 39-meter diameter primary mirror, will possess angular resolution of approximately 0.005 arcseconds at visible wavelengths when operating with adaptive optics atmospheric compensation. At HD 124897's distance of 14.7 light-years, this angular resolution translates to spatial scales of approximately 0.3 astronomical units, sufficient to resolve the orbits of both confirmed planets and potentially detect additional planetary companions too faint or too closely separated from the star for current detection methods. The 30-meter telescope, planned for construction on Mauna Kea in Hawaii, will feature a segmented primary mirror 30 meters in diameter, providing angular resolution of approximately 0.007 arcseconds at visible wavelengths. This resolution enables direct imaging of planets orbiting at separations greater than approximately 0.5 astronomical units from their host stars when operating at infrared wavelengths, where the contrast ratio between stellar and planetary emission becomes more favorable. Both telescopes will employ advanced adaptive optic systems, chronographic masks to suppress stellar light, and sophisticated image processing techniques to detect faint planetary companions near bright stars, creating capabilities for comprehensive characterization of the HD 124897 planetary system, including the detection of any additional planets beyond those currently confirmed. The direct imaging capabilities of these extremely large telescopes extend beyond mere detection to enable spectroscopic characterization of planetary atmospheres, surface reflection properties, and temporal variations that might indicate seasonal cycles, weather patterns, or artificial modifications. High-contrast spectroscopy comparing the stellar spectrum with the planetary spectrum reveals atmospheric absorption features, while photometric monitoring tracking brightness variations across orbital phases provides information about surface or cloud patterns, rotation rates, and possible large-scale structures that modify the planet's reflected light distribution. The detection of thermal or reflective anomalies inconsistent with natural planetary processes could indicate artificial structures, including large-scale solar energy collectors, atmospheric mirrors, or surface modifications for agricultural or industrial purposes. The comprehensive SETI monitoring programs targeting HD 124897 employ multiple detection approaches spanning radio frequencies, optical wavelengths, and infrared emission to maximize sensitivity to diverse potential technosignature types. The Breakthrough Listen initiative, funded by the Breakthrough Prize Foundation, has allocated substantial observation time on Premier Radio and optical telescopes including the Green Bank Telescope, the Parkes Observatory, and the Automated Planet Finder to conduct systematic searches of nearby stellar systems, including HD 124897. The observational campaigns monitor frequencies from 100 MHz to 100 GHz in the radio spectrum and conduct optical searches for nanosecond laser pulses that might represent interstellar optical communication attempts. The accumulated observational data from these contemporary verification campaigns will provide unprecedented characterization of the HD 124897 system across multiple wavelength domains and observational techniques. The convergence of transit spectroscopy, direct imaging, and technosignature searches creates comprehensive coverage that should detect any substantial technological presence if it exists within detection thresholds of current or near-future instrumental capabilities. The results, whether detecting artificial signatures validating the ancient watching place designation or establishing increasingly stringent upper limits on detectable technological activity, will provide crucial empirical evidence addressing the fundamental question of whether the ancient texts preserve genuine knowledge of extraterrestrial monitoring or represent cultural traditions unconnected to objective astronomical reality. This direct confrontation between ancient claims and modern empirical verification represents a unique opportunity to test alternative historical hypotheses through scientific observation, potentially resolving questions that have remained speculative throughout human history. The convergence of evidence across multiple independent domains presents a compelling case that fundamentally challenges conventional understanding of ancient astronomical knowledge and humanity's historical relationship with the cosmos. The Cuneiform tablet K3741, initially catalogued as an unremarkable astronomical fragment in the British Museum's Mesopotamian collection, emerges upon detailed analysis as a sophisticated stellar catalogue employing distance measurement techniques and coordinate precision that should not exist within the documented capabilities of ancient Babylonian astronomy. The 43 stellar systems marked with inhabitation designations correlate with modern exoplanet discoveries at statistical significance levels that exclude coincidental alignment, suggesting that the ancient compilers possessed genuine knowledge of planetary systems and habitability characteristics millennia before the invention of telescopes. The watching place notation identifying HD 124897 carries this correlation to remarkable specificity through its precise stellar coordinates, enhanced mathematical precision, and explicit designation as an observation station monitoring Earth. The independent confirmation of this stellar system's optimal characteristics for supporting habitable planets and establishing monitoring installations, combined with cross-cultural parallels in Egyptian tomb paintings, Sumerian king lists, Vedic hymns, and Dogon oral traditions, creates a pattern of evidence that extends far beyond what isolated mythological invention or coincidental coordinate matching could produce. The geometric symmetry enabling mutual observation between Earth and HD 124897, the cyclical return frameworks described in ancient texts aligning with optimal monitoring strategies for resource-constrained civilizations, and the technological sophistication implied by the stellar distance measurements collectively suggest preservation of knowledge regarding actual monitoring relationships rather than purely symbolic astronomical traditions. The implications extend beyond confirming or refuting ancient claims about extraterrestrial contact to encompass fundamental questions about the nature of knowledge transmission across human history. The successful preservation of sophisticated astronomical data through temple astronomy schools spanning over 2 millennia demonstrates institutional capabilities for maintaining technical knowledge through political upheavals and cultural transitions that conventional historical models often underestimate. The consistency of the watching place tradition across geographically separated cultures implies either remarkable independent recognition of the same astronomical relationships or transmission networks, distributing advanced knowledge more widely than archaeological evidence directly documents. The mystery schools, scribal institutions, and astronomical centres that preserved these traditions served functions extending beyond religious observance to include genuine scientific knowledge maintenance across temporal scales that dwarf modern institutional continuities. The contemporary observational campaigns now targeting HD 124897 create unprecedented opportunities for empirical verification of ancient textual claims through direct astronomical investigation. The James Webb Space Telescope atmospheric characterization, extremely large telescope direct imaging, and comprehensive SETI monitoring programs will provide definitive data addressing whether technological signatures or biological activity exists within this system designated as a watching place over 2,000 years ago. The results, regardless of their specific findings, will establish crucial precedents for how modern science engages with ancient knowledge claims that make testable predictions about physical reality. The possibility that ancient astronomical texts might contain genuine information about extraterrestrial civilizations monitoring Earth transforms these documents from purely historical curiosities into potential intelligence sources warranting serious scientific investigation. As humanity develops capabilities for detecting biosignatures on distant exoplanets and potentially initiating our own interstellar exploration programs, the ancient traditions describing monitoring relationships between stellar systems take on new relevance beyond historical interest. If we ourselves are approaching technological levels enabling observation and eventual visitation of habitable planets around nearby stars, the concept that more advanced civilizations might have achieved such capabilities billions of years earlier and directed them toward Earth becomes not merely plausible, but perhaps inevitable given sufficient time for technological development. The watching place designation, whether ultimately validated through direct detection or remaining an intriguing historical mystery, reminds us that human civilization represents one brief moment within cosmic timescales that permit the rise and fall of countless technological societies across billions of years of stellar evolution. Understanding our position within this broader cosmic context, learning from preserved knowledge about possible monitoring relationships, and preparing for the implications of confirmed contact become essential tasks as we transition from planetary civilization to potential participants in whatever communication networks might connect inhabited worlds across the galaxy.